I'm here today to give a tutorial. I was asked not that long ago, so this will be fun. We're going to talk about LLVM and OpenMP. So LLVM, the compiler, and OpenMP inside of that compiler framework. So I'm trying to make this, it's a mixed bag. I have everything. I have things for application developers. I have things for OpenMP developers, for people that do compiler development or just use compilers for all I care. If you have questions, please speak up, because to make the most out of this, especially given the number of people we have, and that includes the people on the Zoom, we could just discuss things. If they're unclear, or if you have questions or follow-ups or whatever, just, speak up. We're like 12 people. Cool. So, so you might ask yourself, why am I standing here giving you this talk, right? So let me start a little bit about me. So I got a PhD from Germany a few years back. And then I moved to the US, worked at Argonne in Chicago for a few years. And last week, which made this entire enterprise a little bit, funny business, I'm currently switching jobs and I'm giving a presentation. So last week I joined Lawrence Livermore and I moved, and everything is out of the ordinary right now. But I've been working on LLVM for 8 years now, and in the OpenMP standards committee for for 4. And effectively, last year, I'm the official code owner of OpenMP offloading in LLVM. It doesn't actually mean much, but it sounds cool. Okay, so LLVM. Let's do intro. Who here knows what LLVM is? Has used LLVM, something like that? No, few people.
Yes.
Thank you, Kent. So LLVM is a compiler framework, effectively. So it comes with various subcomponents, subprojects that provide you everything from a front end for all the C family languages. So a front end that is able to, take any C-like language as an input, not any, but a lot of them, to OpenMP runtimes for various GPUs, for other accelerators, for CPUs. It comes with an own C++ standard library, and they're building a C standard library. It comes with a debugger. It comes with various other subcomponents that I'm not going to list now. Okay, so it's open source. So it's kind of the competitor to GCC, if you want to see it like that. And don't get me wrong, it's good that we have two. It's great to have competition between the two. That helps to advance them both. It's extensible, so you can actually, if you have a problem with it, you can go into it and you can fix it, or you can extend it and add your research part to it, or other things. It supports like all the major CPUs and all the some of the GPUs so far, and the other GPUs are coming. And it's not as good on the kind of minor or exotic CPUs as GCC is. It has support for C, C++, and new standards. SQL, HIP are implemented in there. It supports CUDA. It supports OpenMP, OpenMP offloading. There are efforts to make support OpenACC and so on. So it's like a lot of languages that can kind of be compiled into this. You obviously get the coolest features if you use it, and we'll talk about some of them later. And then, obviously perform it incorrect, right? What compiler isn't correct all the time? Okay, so how does this work? The 101. You take a C file and you use this C frontend, the C language frontend, C-lang or Clang, depending on which camp you are. You use it to generate LLVM intermediate representation, LLVM-IR. Okay, LLVM-IR, there is a nifty tool called OPT, that allows you to run passes and analysis on LLVM-IR and produce LLVM-IR again. That's not how Clang would generate, object files or executables, but it's good for you to use if you want to try out stuff. Once you have the done on the LLVM intermediate representation, you can generate LLVM machine intermediate representation with LLC, and then you can optimize that too, but I'm not going to go into detail there. And then you can generate actual machine code for whatever your target is. Okay. So my work is almost entirely focused on this part, with some extensions into Clang and very few things in the backend part. Okay, so there's a couple of these overview slides that you will probably just look up again. I mean, there's little point in remembering everything. There will be, a lot of content. This is supposed to be 3 hours, and I had to kind of gather all the things I have. So this is, gives you an idea of how to configure and build LLVM by yourself such that it is OpenMP offload capable. So these two commands up there should suffice to get an OpenMP offload capable LLVM. So if it technically doesn't even have to detect CUDA, but it's better if it does, and or the ROCm stack. So a couple of important options, things that you should try out. There's a lot of documentation on this. For general LLVM stuff, go to the LLVM docs, which are usually fairly good. The OpenMP docs are not as good, but we're working on it. And we're always happy if you have input to the FAQ or other things that you want to put there. Okay, again, one of those slides. So what to do if you actually work with LLVM. So anyone here ever developed LLVM, built something, added something, or tried to, improve a pass? Okay. Couple of ideas. If you do so, CC Cache, Ninja, and a fast linker will make your life much easier. Share libraries as well. If you're looking for just general application development, always consider LTO. And we'll talk about device like GPU LTO later. LTO means link time optimization. So at the point where you see the entire world, you can do better optimization than if you only see a little part of it. Use the good flags like O3, OFast, mArch native whenever you can. Sanitizers are a great thing to debug your code. Documentation is there, even if you have to look for it. And we'll get to more ways to get information later. And the last one of those at this point. This is if you do OpenMP offloading, especially, given that this is, an OpenMP event, I'll figure to include some information there. I would always go with a very recent compiler. If you come to me with bugs or problems or performance issues in LLVM 14, I'll probably tell you to first show me that it happens in the current build before I'll do anything else. Because whatever happened, half a year ago is in the past. We don't have the manpower to really, port back everything. So if it's critical, we port stuff back, but we can't do, performance movements and so on. So really, and we're moving actually quite fast in terms of changing things. So we break stuff and we change things quite fast. So sometimes it's just like, oh yeah, that is just the way it is. Then we have a lot of these. And we get to them later in more detail. We have optimization remarks. You should certainly know if you do OpenMP offloading with LLVM. The other compilers have those too. So you really want to know. You have these environment variables that help you to get information out of the compiler into runtimes. So there is profiling built into LLVM offloading that gives you Chrome tracings, and we see that later. There is these libom target info that gives you a lot of information. For example, it tells you when is data sent to the device and when not. Or it keeps track. It basically shows you how we keep track of the ref count of data and so the reference count to determine when data has to be shipped or doesn't have to be shipped. How we execute a kernel. What mode do we use? How many blocks and how many threads do we use? All of that information that is kind of hidden behind this world of whatever the runtime does can be exposed through these environment variables. And if you need more information than that, for example, if you want to enable the runtime assertions or other things, there is even a kind of two-step process to really make the runtime try to verify things are going well. And it's a two-step process because it has to be free in normal runs. So while printing a little bit of information in libmap target about how we started the GPU kernel or how we move data, that is just a printf somewhere. That's pretty much free compared to moving data. So it's okay. Especially if you don't enable it. Like there's an if, then print. Cool. But if you embed debug information, the runtime assertions into your GPU code, that's pretty much not free. Because now we have printfs in GPU code, ain't free at all. We have conditionals in GPU code, also not free. So that is a no-go cost overhead. And that is why we have a two-step process here. And I'll explain later how this works, because that trick also works. Like you can basically copy that trick and use it yourself. We have a single runtime. So there's no multi-runtimes. That, like a year or two earlier, LLVM just built multiple runtimes, and you had to configure if you wanted the debug runtime or the non-debug runtime, and then it was always like a hassle. Now it's one, so it's much easier. And then we have quite a few flags, both environment variables, which are always the capital ones, and command line arguments that allow you to tell the compiler to assume certain things about your program, which will make your program usually faster. And we're sometimes talking a lot faster. Why is that? The semantics of OpenMP are what they are, and we have to preserve them. But you actually don't necessarily need all of that. So we do a lot of things for the sole purpose of preserving that semantics, even though you would never need that kind of semantics. You're fine with a relaxed version of it. And that is, if the compiler can't figure out that the relaxed version is fine, you have to help the compiler. And that's why we have all these flags. And now I screwed up. How did I screw up that bad? Last flag here, and we see most of them again later on, but I figured repetition helps to remember. LTO is link time optimization. And since LLVM 15, which is released now or is about to be released, you can turn on link time optimization for device code, like GPU code, if you compile it as HIP, CUDA, or OpenMP offload. So we basically enable it for all three. And that is, even if you have all your kernel code in one file, that still can improve your performance substantially. If your GPU code is spread across different files, this will probably make huge impact. So as soon as you have like an application that spreads the GPU code across various files, because your application is big and you want to write it modular, this is a game changer. And we have some numbers on this for applications, real applications that use OpenMP offload. Okay. What do you do after this thing is over and you want to, ask questions, get involved, do things? Various ways to ask the community to get in touch. We have the mailing list alternative, which is the discourse. We have various kinds of chats. So I monitor discourse to a large degree, and I hang out in IRC in case you ever want to chat with me. We have these meetings, like a weekly OpenMP and LLVM meeting. We have meetings about ML in LLVM, like machine learning in LLVM, yada, 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 lots of things. Check out the Getting Involved page. Almost everything is kind of listed there. LLVM 15, I mentioned that earlier. It comes with quite a few goodies with regards to GPU offloading and OpenMP GPU offloading. So we got a new driver. Like if you think Clang, and if you ever used Clang, or GCC for that matter, what you're actually using is a driver, not a compiler yet. The first tool is a driver that basically takes a look at your command line arguments and decides how to build a tool chain of things that have to be done. Like, what tools do I invoke? What intermediate files do I produce? How do I chain things together to create the output that is desired? And so this driver, we kind of, let's call it, fix that for all the offloading languages. Now, OpenMP, CUDA, and HIP. CUDA and HIP is opt-in for now. OpenMP is the default, so you can't opt out anymore. We deleted the old one. So we're kind of confident in it. It allows you to do multi-architecture builds. So you have a single executable that runs on your NVIDIA card and your AMD card. You can just move the executable around or static library. It allows you to actually have static library support now. So that was a long time coming. And when like all of this is about, offloading, like static libraries that have GPU code in them, not static libraries like CPU only. That obviously kind of easy. But the whole part about like how you get GPU code to work is kind of hard because we have to embed everything in the existing pipelines. But we added these GPUs, these additional architectures, but everything in between stayed the same. So we only, for example, you only generate one object file for each source file. I mean, if you only have one architecture, it's easy. You could just like compile it to an object file. But what if you have now 5 architectures? What do you do with that? How do you kind of make all of this happen? We have the link time optimization. You can now mix you can now mix OpenMP, CUDA, and HIP. So you can call a CUDA device function from OpenMP target offloading. So if you happen to have some old CUDA code lying around you really want to reuse, not a problem. You can also use that to do low-level programming, right, with CUDA or HIP. And then a lot of these flags that we get to. Okay, so now we'll talk about LLVM OpenMP. While I'm here giving this talk, tutorial, it's obviously not me doing all that work. I mean, barely. We have a lot of people in academia, industry, and like power users from all over the place that help. So that report things, that test things, that do development, do researchy things, and so on and so forth. You should feel free to reach out. We always have fun projects and little tasks to get started and so on and so forth. How to get involved with LLVM OpenMP specifically. I mean, there's our webpage that has like an FAQ and some information. We have a weekly meeting that is attended by all the industry and all the researchy people. The industry attends because they build on top of that their industry compilers. So the HPE Cray compiler, Intel compiler, AMD compiler reuse to different degrees what we're building. So they come and try to talk to us, make sure that they know what's going on. We have office hours once a week or every 2 weeks. It depends on how you look at it. We have a discourse category. It's like a mailing list. And then we have a Slack channel for OpenMP optimization. So where we discuss, everything from generic OpenMP questions to the papers usually have channels there, and then oh yeah, we'll write papers and researchy things and so on and so forth. All right. How did this work? Oh, sorry. Actually, it was fine. Oh yeah, and then it took me a second why this is here. So why do you want to get involved? I copied this out of a paper we wrote with some nuclear physicists, and don't quote me on it. Maybe they're other kind of physicists. Who knows? So they have this app that is called OpenMC, and it actually uses OpenMP offloading as their main model of getting onto the supercomputers. Okay, and they had really bad performance, like really bad, when they used LLVM. So they came to me and like, hey, I mean, this is like absurd. So it's really that low that a CPU blows this out of the water. So something is wrong. So we looked at it. And then I looked at the app with them, and we basically played around with it for 2 weeks, roughly. And at the end of the day, our speed up from the very beginning to what they had at the end of those 2 weeks was 97x, which made it actually bearable to run it, like 2 orders of magnitude. We can start talking now. And then that was afterwards, more things were added. But after like 2 weeks of just going back and forth. And the first thing we did is CMake Unity build with a speed up of almost 13x. Anyone knows what a CMake Unity build is? That's poor man's LTO. So if you don't have LTO support, for whatever reason, or you can't do it or whatever, you use Unity builds. Effectively, what it does, and CMake actually comes with support for this nowadays, it copies all your source files together into a single one. So those are Unity builds. There's other ways of getting Unity builds, but CMake comes with support. So they have their source code spread across a lot of files. And I looked at it and I'm like, yeah. I looked at our remarks that we emit and I'm like, yeah, we can't optimize anything here because we don't actually see the code. We see only, a fragment of the code here and a little bit of the code there. The compiler is like, I have no idea what's going on. So I'm have to be conservative all over the place, and the performance was really bad. So more than an order of magnitude by just exposing all of the code to the compiler, and then the compiler is like, oh, I see what you're doing here. Let me help you. Okay, so Unity build. Then they found a problem with our update clause, which was like a performance bottleneck. So they put the profile on, and it just showed up like in huge chunks. Update. Why does update take that long? So we run a host profiler, and it was in one of those trying to update some maps internal to the runtime, and it took forever. So we went and looked, and I fixed that, and then another 8x speed up and so on. And then obviously at some point you don't get the big speed ups anymore, but it's still, if you multiply it up, it actually still helps you to get another 30%, another 10%, and so on. It helps, it adds up. And I think the first, oh my God. Yeah, all of these speedups are more or less by working with us and looking into the IR, looking into like profiles and so on and so forth. Everything afterwards was them doing some magic on their algorithms. So there is huge potential in a lot of apps, and we already know a lot of, less good, less performant parts. And then we can look at your app and you can say, okay, this is ways to improve it. Or now we can prioritize your problem and actually kind of fix the parts that we had on our list for a long time, but nobody ever came to us. So we just, worked on other things. Again, this is for reference only. If you want to go back at some point and you're like, okay, I want to really know more about these things, or I want to cite them in my papers or whatever. This is a selection of the last roughly 3 years of papers that we wrote about all these things. So we have a lot of students, researchers, PhDs that work with us. We actually write papers about what we do, and we still put it into LLVM and ship it. And it also goes into vendor compilers. So what we do is both research, but also development in production development, that people actually ship this, which can be great in case you're interested in a career, in R&D, or go to vendors afterwards, but you still have to do research and papers for now. So let me know. All right, OpenMP and LLVM. If you think OpenMP in LLVM, you usually think pragmas. You think the C front-end Clang has a pragma parser and then a semantic analysis for those pragmas that determine if they make sense, and then it generates code for those pragmas, like runtime calls into, in some other code. That's what people think if they think OpenMP in general. They think pragmas. But as you can see, there's a lot of white space here. That's not all there is if you think OpenMP and LLVM. So some people might come up with, wait, there's runtimes involved. There's libomp or libgomp if you're in GNU, and there's other OpenMP runtimes that actually do, spawning threads, doing all these runtime functions have to go somewhere. So all of that logic lives in libomp. It's a classic runtime. It exists for a long time. It runs on the host, right? So this is, OpenMP 3.1 or something. That is roughly the state. Nowadays, you have way more runtimes. You have libomp target plus plugins. Both of them run on the host. Both of them are needed to do OpenMP offload, at least with LLVM. And then you have libomp target minus architecture. That is a runtime that goes with the application onto the device to provide that runtime support on the device. Because in your target code, you also call get thread num, get num threads, all of those funny things, right? I mean, they have to be resolved somehow. So there has to be a runtime that answers those things. And that is part of this offloading device runtime. Then, because we now get a second front end for OpenMP, which is called Flang, Flang, Fortran, right? We decided that it is time to unify the code generation for both. So we have this OpenMP builder thing that lives in LLVM that helps us to just generate the same code for OpenMP, regardless if you come from Fortran or C, which is a good thing because normalization makes things easier and you get the same optimization, the same performance, the same results if you write a parallel for loop in either language, which is better than the alternative. It's obviously not done. It's a work in progress as we move along. But so that you have ever heard this. And then this is kind of the funny part that we added. It's an optimization pass in LLVM that is run if you run LLVM with 01 or 2 or 3 or fast, right? If you turn on optimizations, this pass is run always by default. It will detect if you run code that has been compiled with -f OpenMP. So if OpenMP is enabled. If not, it will just say, oh, I'm out of here. Nothing for me to do. If you run with OpenMP, it will actually do optimizations, and it will do high-level optimizations that are OpenMP aware. And it's the first kind of pass of this kind in one of those, compilers that we officially know of. It knows what the OpenMP runtime calls do. Why? Because we taught it. It knows how to rewrite a program structurally, and we'll see that later in various things. And it has very powerful interprocedural optimizations to especially optimize device code, where it's really important that you really get it right. Before we go to the extensions and like researchy things, let's see where we started with all of this. Oh wait, let's first make it quick. Any questions, comments, concerns right now? And feel free. Anyone on Zoom? No? Okay. I'm just assuming I'm explaining so well that you all get it. So this is how we started a few years ago to start to improve LLVM OpenMP. So because, there was a lot wrong with it and you had to, prioritize. So the first thing we looked at was debugging challenges, because even if you just do, an optimization or whatever, you break things because your optimization is wrong at the beginning, or you didn't account for the corner cases, and then things break. And the way people debugged OpenMP offloading code was so horrendous that we said, okay, before we do anything else, we'll start looking at that. It's still not great, but it's a little better. So back in the day, what happened is when you run a program and it crashed on a device, you got the first line here, maybe the first two, something. So it said CUDA error, an illegal memory access was encountered. That you got that when you were lucky. Now, what you get nowadays is roughly this message. So first of all, it tells you where it crashed, like source locations. It's a thing, which is kind of cool. And it also tells you about this web page where you can now get more help on how to debug this in the first place. Because, by default, we can't enable all the debugging stuff. Again, costs. So you have to, if it crashes, you go back and then you enable stuff and then things. So what can you do? For example, you can look at the libom target info flag. I mentioned that earlier. It's a bit set. That you set different bits and they enable certain information from the runtime to you. Here, if you enable it and run it, what it tells you is for example, that it starts this kernel, and the kernel has 3 arguments, and it tells you that one of the arguments is called n. It has 8 bytes, and it's an implicitly passed argument. So you didn't map it, but it is just captured in the region. And it's captured as first private. And then there is this to from something with 8 bytes. And then there is the to. So it tells you what the arguments to the kernel are, how memory is mapped, and so on and so forth. Especially important about the implicit things that you haven't specified yourself there, as the name suggests, implicit. It also tells you when it actually does the copying of things, names of variables, and so on and so forth. And then here, one of my fan favorites is launching kernel. this is the name of the kernel, which is not great, but just for reference, at the end of this funny little name, you can find the name of the function in which the target region is in. This is C++, so it's C++ mangled. If you put this part into C++ FALT, it will tell you this function is called sum. And the target region is in line 5 of the source file. So that's what it tells you. So that is how you kind of can find them and identify them. And we need all of this part to get unique function names, because you don't want clashes. How many blocks did we start? How many threads did we start per block? In what mode did we execute? SVMD mode. SVMD mode is great. If you see that, you're good. If you see generic mode, not so good. Okay. Now you have this ability to turn on debugging. Debugging has also, it's also a bit flag. I think right now it supports 3 different bits, but more coming as we go along. Show that yet. This is a 2-step process. I mentioned that earlier. First, you turn it on with a command line flag. It's not only an environment variable. libom target info, you can take any executable you built before, turn libom target info equals to 16. It tells you how the kernels are started. Nothing else is needed. For debug, you actually have to compile it with a bit set at compilation time. And only those bits are activated. Only those bits can be activated through the environment variable at runtime. So only here bits, 4 and 1 at that point. And then at runtime, you can actually activate them with the environment variable flag. And then it tells you here 2 things. It tells you shared memory stack is full, which sounds bad and is bad. It also tells you about the impact on performance, so really not cool. And then the next thing it tells you is malloc return a null pointer. And you can imagine things go downhill really fast after that. And that is where our memory access problem came from. So this is on an AMD. Oh no, this is on an NVPTX, but just malloc return a null pointer. On an AMD, right now, we don't have malloc support, so it will always return a null pointer. So one of those things, right? But at least you get some information about common problems out of the runtime to help you debug things. There's also some support to do tracing through the device functions. But yeah, that's a little iffy. Okay. Now, how do we do this trick? And you can use the same trick to optimize your applications to kind of put in behavior that is potentially costly, that you can eliminate at compile time. And we use this trick all over the place for the entire runtime, not only for the debug stuff. You basically create a constant expression, like a static, an internal constant value, global value. And I mean, for us, we feed it with whatever you put into that debug, into that command line flag. But for yourself, you could just initialize it with a value. And then everything that is guarded by these bits is optimized away if those bits are 0. So you basically write dead code depending on what the value is. And that dead code is usually, we're usually pretty good at optimizing dead code. So this is really free. So this is how we enable a lot of things, just as FYI. Okay, so technically, before we looked at the GPU stuff at all, we looked at OpenMP overheads, especially indirection overheads. And I've used these slides since 2018, exactly these slides. And the last time I checked is probably last year at some point, and it was still true. But you can check again and see if your compilers evolved over time. The idea is as follows. You have a program, you set y to 7, then you use y inside of a loop and after the loop, okay? You would assume an optimizing compiler replaces y with 7. Yeah, that's what every compiler, when you turn on optimization, will do for you. It's great. That's what we want. Now, we're living in the day and age of parallelism, so let's parallelize this loop. Easiest way on parallel 4, okay? And then you would still expect that the parallelizing compiler helps you out, right? Y is still always 7. Nothing has changed except that you made this loop parallel. What will unfortunately happen is that Y is not replaced by 7 inside the parallel loop, but surprisingly, usually also not outside the parallel loop. So it's great. So by introducing parallelism here, you basically blocked optimizations. Yeah, so far so good. Does it matter, right? I mean, there's a lot of optimization that we perform that don't matter. A lot of normalizations. And as long as you don't have actual evidence that something actually matters, it doesn't. So we can assume it doesn't. Now, to determine if it matters, I did an experiment. So I ran the sequential version of some of those very simple OpenMP benchmarks against the OpenMP version. But so I turned on OpenMP, right? One time sequential version is I turned OpenMP off. Parallel version, I turned OpenMP on, but I used the environment variable to make it run on one thread. So sequential versus OpenMP on one thread. Okay? If OpenMP is free, you get the same performance. If there is some cost to OpenMP, you'll see it. That doesn't necessarily mean you don't know where the cost comes from yet, but you can measure the cost of introducing OpenMP. So Pathfinder slowed down by 40%. That's not great. SRAT version 2 slowed down by a factor of 2.4, basically. So that's not great either. So we basically introduced OpenMP into our app, and it runs it takes twice as long to run. Not perfect. So now people told me, oh, this is because the runtime calls, runtime overheads. That's the reason. That's what they told me. And I'm like, I'm not so sure. So I did an experiment. I took two LLVM passes, ATTR and ArgP. So argument promotion and attribute deduction. Attribute deduction determines things about pointers mostly. So is a pointer read only? Is a pointer captured? Is a pointer write only? Stuff like that. So it determines properties interprocedurally across function calls. So it basically looks at all the call sites and then determines something for the pointer. Argument promotion effectively changes how values are passed from passing them as reference to passing them as value. So if you think about it, instead of passing, an integer pointer and then in the callee, you dereference to get the value, you dereference first and pass the value. The main difference is if you pass the pointer, the value the callee can change the value that it points to. While if you pass the value, the callee just sees the value. That's it. Can't change the thing. Okay, so I took those two passes and I made them aware of OpenMP runtime calls. So we can talk about that later how, but end result is if I only made one of them aware, I got the same performance as I had before, the same regression. If I made both of them aware, I got the same performance as the sequential version. So the entire regression was gone. So there was no runtime call performance hit. This was all optimizations not triggering. Once you teach these optimizations to trigger in the presence of OpenMP, that indirection was gone. I mean, there still can be runtime overheads, but for these benchmarks, there were not. And that was kind of an interesting moment. So we spent some time now throughout to build this attributor interprocedural optimization framework that is able to, by default, natively, by construction, look through OpenMP indirections and other indirections for that matter. It's not only OpenMP. And that runs as part of the OpenMP optimization pass as well. So, yeah. Okay, cool. And then let's go back to GPUs because most people here are probably more interested in GPUs, I would assume. Yes, no, maybe? CPU, GPU? Oh, yeah? Sorry about that. You'll hear a lot about GPU. Yeah, you will hear a lot about GPUs tonight. Sorry. I just don't know enough about
That's GPUs. Good.
Oh, Kent is still here. It's good. I thought I lost you. Okay. Let's talk about the CPU versus GPU execution model, which is which was also a fun thing to think about for a while. So up there, you see a CUDA kernel launch, where the kernel is called func. We start one block. We start 4 threads, and we pass args to the kernel. That's more or less how a CUDA kernel launch looks like. Down here is what you would kind of a somewhat equivalent code for OpenMP, where we start a kernel like a target region with one team. One block is kind of corresponds roughly to one team. Then we have some code in that, and then we call in parallel this func with 4 threads, and then we have again some code. So it's a little bit different because these things are not part of the CUDA world. But I need them to explain what the problem here is. When you execute the CUDA code, what happens is all threads start. All threads execute the kernel. All threads stop. That's what happens. It's like SVMD by design. Everything runs at the same time. If you want things to not run, you have to guard it. You have to say, if your thread ID is 0, then execute this code, otherwise don't. If your thread ID mod 2 is 0, then do this, otherwise do. So you're in charge. Everything runs at the same time. What about the OpenMP code? In the OpenMP model, once you enter a target region, there is one thread, the main thread, that runs conceptually. Okay? Both. That's the fun part. OpenMP never changed the model when it went from a CPU to a GPU. So the model is the same. And that gets us to the problem in a second, right? So conceptually, there is one thread, the main thread executing A, the block with the color, whatever black here it is. And if, at the end, there's one thread, the same thread that executes B, the block in yellow. And in the middle, there is this parallel region. That is where OpenMP says, these threads come into existence. They come from the ether. The team is, created. And then you have these threads that execute this func together, with the main thread being the first of them, and then its team of up to 4 threads. And you probably have noticed that those two pictures look roughly the same, but not exactly. And the problematic part is what happened here. We're talking GPUs now here, right? The CUDA code looks like this because that is how GPUs execute. That is how GPUs execute code in the first place. They don't have these bubbles where there is no threads. You can't just start threads and stop them. That's not a thing. So you have threads there. You have to do something with them, and you can't just execute A and B. I mean, if A is printf, you don't want it print 4 times. You want to print it once, right? Or if A accesses some memory based on the thread ID, you don't want it accessed based on thread ID like 3, only based on thread ID 0, and so on and so forth. So you can't just execute. So you have to do something with those threads that is not executing, or at least not executing the user code, right? Okay, so earlier I mentioned SPMD mode, and I said that's good. And I mentioned generic mode, and I said that's not so good. In LLVM, OpenMP speak, SPMD mode is this, generic mode is this. Okay? Now, I'm going to explain to you how we go from generic to SPMD mode. I'm also going to explain to you how we implement generic mode, because it's fun. Cool. Let's look at, okay, so this is the first idea you could have, right? You could say, oh, let's do what the CUDA programmer would do. I guard the A and B code, right? I say, okay, if you're thread 0, then execute A. Then I have a barrier so that all threads, are in the same page, because A has to be executed before the parallel region. Then you execute func. So this is roughly how you would translate from generic code to SPMD mode. So you would perform this code transformation effectively. So remember, can I go back? No, I can't. Yeah, this is what we started with. So this is what the user wrote. And we would basically perform this code transformation. So we guard the sequential code, we introduce a couple of barriers, and we effectively hoist the parallel outwards to the outermost, to the teams. So as soon as the parallel and the teams meet, we're good. This is kind of great, except that what happens if A contains a parallel? Before, let's try to go back. If A contains a parallel, you would have expected it to, spawn a couple of threads. Those threads now execute that code in together. Then they, you join the threads again. You leave A. You execute the next parallel. But here, you can't, because the threads are already bound in the outermost parallel, and only one of those threads entered the A code. So now that parallel is, first of all, nested, which it wasn't before. So the environment changed, and you don't have threads for it anymore, which also changed things. I mean, the latter part is actually not that bad. Technically, you can just sequentialize it, but the first part, the environment changed, is problematic. So if inside of A, you ask, hey, how deeply am I nested in parallels? The answer might change. That's not good. And then the second problem is what happens if you have a barrier in there? Why is that a problem? I mean, you guarded it. Only one thread will reach that barrier. Not a good idea. That will deadlock. So the generic mode to SPMD mode transformation doesn't always work. So you basically have to look out for these and a couple of other fun things. But once you determine that those don't happen, or you can deal with them one way or another, you can move generic mode to SPMD mode by doing this transformation. And OpenMP OpPass will do that for you. Oh yeah, we do that, since LLVM 14-ish, I think. What am I looking at here? Oh yeah. Let's look at how we execute code if we have generic mode. Okay. If we can't get rid of generic mode, we execute it as such. So the main thread is actually going to execute all the code, which makes sense. That is what it does here, right? So the main thread, thread number 0, is like conceptually thread number 0. It's not actually hardware thread number 0 on the GPU, but that is a different story. It is conceptually thread number 0 from the OpenMP world. So if you ask, hey, get thread num, you always get 0. That thread is going to execute all of the code, while all the other threads are going into like some state over there. And then we introduce these barriers at the beginning and the end of a parallel region. And at that barrier, we are going to tell all the other threads that are waiting in that bubble over there, hey, the main thread found a parallel region. You're up. We need your help to execute this parallel region fast, in parallel. And then you basically have to tell them, as I've tried to do with the colors here, what parallel region you found. Could be a lot of them, right? You might not even know all of them at compile time. It could be in static libraries and so on and so forth. So you have to tell them here, this is the parallel region we found. Here are the arguments that you need to execute that parallel region. Go for it. So then they will execute that parallel region. They'll hit this other state. And then they will tell the main thread, hey, we're done. Once everyone is done, you can continue. And then they go back to waiting for the main thread to tell them what to do. So effectively on the right, we call that our state machine. So this is just a state machine that has effectively 2 states. Waiting for the main thread to tell you what to do, doing it. If the main thread signals you to do something, but it sends you effectively a null pointer as what is the parallel region. So that means you're done. You can exit the program now. Oh yeah. Now, what is the problem with this? I kind of hinted towards that. You have to identify what parallel region to execute. There might be a lot of them, and you might not know them at compile time. So the only way to identify something that is kind of unknown to you, really, is to give it the function pointer that contains the code of the parallel region. So effectively pointing at the code that they are supposed to execute, because you can't name them beforehand. So these are function pointers that we pass around. Have you ever thought about what happens inside of an optimizing compiler if you start to take the addresses of functions and pass them around? The answer is not that much anymore. They don't like that at all. Passing function pointers around prevents you to do inlining, prevents you to do interprocedural optimization. Really not a good idea for performance reasons if the compiler is not able to undo it all. So, okay, here, that's what I kind of just said. So we use function pointers to identify these parallel regions. Now, that's bad for performance, so let's come up with a different scheme. So OpenMP op tries to avoid this. OpenMP, like by default, we use function pointers, but OpenMP op tries to replace them with other IDs. So what we do is effectively, this is the code as we generate from Clang for a generic parallel region. It's not actually what Clang generates, but it's a high-level view of what is executed. Most of this code actually is inside of our device runtime. So Clang actually only generates 2 runtime calls. Everything else is, everything else is in the device runtime. But to see what's going on, I inlined everything into, high-level C code. So this is just. So what happens? Kernel is started. The threads determine if they are the main thread or the workers. The workers go into the state machine, waiting. The main thread executes the user code. This is the user code. User code in this case is just a parallel function, a parallel region, which then is outlined into a function. So the content of the parallel region is inside of par func. What we do at the beginning is we inform the workers. Here, par func is the parallel function that we encounter with the main thread. Here are all the information you need to execute it. Then the workers and conceptually the main thread execute the parallel function together, which again, conceptually, not in reality, but doesn't matter. And then the main, we have to, the workers realize they're up. They get this inform will correspond to the wait. The workers know what to do. The workers will execute that function that they were passed. Then they will tell the main thread that they're done. Main thread is waiting for everyone to be done. And the workers go back into their waiting state, and the main thread continues executing the user code. Now, what we actually want to have is something like this. We create a function ID. It's effectively an address. It's a character for the sake of a character as small, because we only use its address anyway. We don't care. I mean, the content doesn't matter. Content is undefined. But the address is what gives it a unique value. And so we use this, and instead of passing the function pointer, we pass that ID. Now, this is not always possible because, I mean, I can always create one of those addresses for each parallel region. I can always pass it to the workers, but the workers now have to do the reverse from the ID to the parallel function. And if I don't know all the parallel functions in advance, how do I do the reverse? So you can only do this if you kind of know the parallel function and you can rewrite every use. And then instead of just passing the function pointer, we pass this ID. And then here we check if it is that ID, then we call par function directly. And if not, we call whatever we assume it's a function pointer because it has to be, otherwise we're screwed. So we'll call that function pointer. And we're not only doing this optimization nowadays in LLVM, in the OpenMP op pass, but we also manage to, if we can't do SPMD mode, so if we can't go to SPMD mode, we do this, and we also try to get rid of this indirect call as well. So if we determine that all the potential parallel regions that you might call are known, we don't need that indirect call anymore, which is also a good thing. It saves time. Mm-hmm. Just not having certain dead code actually helps you improve performance. On the CPU, not so much. On the GPU, for sure. Okay. Yeah, this was a just excursion into something like a little low level. Yeah. Cool. What am I looking at now? I have no idea. Oh, yeah. So the problem now is it's not only if you know all the parallel regions or not. The problem is also maybe those parallel regions are used by multiple kernels and you don't see all the kernels. So I see here in this code, I see the parallel region just fine. It's a static function, so I know all the uses. This is the only use. But the problem is this function is visible. So some other kernel that I don't see might call that as well. So I can't actually rewrite it because I would need to change the state machine in that kernel as well, and I can't, right? Except if I turn on LTO. So this is one of those problems. And this is one of the first times we see these assumptions that we have. And this is an assumption you will probably not need, but we use in the runtime, but it gives you an idea about how to utilize these assumptions. So OpenMP in 5.1 introduced pragmas to give the compiler assumptions. And one of those that we use is OmpX, like an extension to the OpenMP fixed assumptions, no external callers, and it effectively just tells the compiler, hey, no one else is going to call this, and from the outside. So all the callers are actually internal. You could deal with it in different ways. It's just an example. If you use LTO, you will for sure never use this. But it's just one example of assumptions. We have other assumptions. We have assumptions about, you can tell the compiler that assembly code inside of your application is not going to actually have call semantics. Because assembly code is scary. It could do all sorts of things. And we're not going to analyze it anytime soon. So if we see assembly code, we kind of assume the worst. But you're allowed to tell the compiler, hey, this is assembly code. It will figure out, it will do things, but it will not call a different function, for example, which we will use to determine like better optimization. So those things are, helpful and important. What did I do? I broke it. Okay. Now we're going to questions first. Oh, are we on time? Oh, we're in. Okay, I'm really slow, but that's fine. We're going to go through an example here, how we get the same PTX, so low-level code, that when you use OpenMP, that you would get if you use CUDA, which has not always been the case. Nowadays, it's actually possible. It doesn't always happen, but because we haven't, not everything that I'm going to show you in optimizations has made it into actual LLVM. Some of it is still, more on the downstream side, but most of it is. So I'll walk you through effectively how you remove all the OpenMP abstractions that we have to put in place to support arbitrary code to get to the bare bone performance that CUDA gives you, because it never started with abstractions to begin with. You had to manually do all the things, and now OpenMP goes the other way. The compiler, the runtimes do all the things for you, and we now kind of try to make it fast. So let's see how we end up at the same place. Yeah, this is my example for this part. It's a CUDA kernel where you manually allocate some buffer into a local shared memory, or shared space, or whatever you want to call it, depending on what language you follow. So you have to manually say, hey, this buffer actually is not like a local buffer for my thread, but it's a buffer that is shared across the entire team or the entire block. Then you have a local variable, which is thread internal. It cannot be accessed by other threads according to the CUDA specification. Then you have some code where you manually did, check the thread ID and guarded it to be sequential, some initialization stuff. You sync all the threads manually. You have some code that is executed by all of them in parallel. And then depending on the ID, they do different things, they access different data. You synchronize again. And then for some of them, you do another parallel work itself, okay? Questions? Cool. Yeah. Yes. Inside of one block. Yes. So all the threads in one block are going to, wait there until everyone hits its barrier there. All right. How would you write this in OpenMP offloading? You do a target teams distribute with a grid size and a block size right. That way you basically spawn as many teams as you have blocks in the CUDA world. Okay? I mean, we don't see how the CUDA code is launched, but it would be launched with effectively, grid size and block size as parameters. So this is how you get the same number of blocks in the OpenMP world. So now, I aligned it. So you see what matches, right? So we have this loop is implicit, like the grid loop the I loop is implicit, but we don't use I anywhere, so it doesn't really matter in a CUDA world. It's your block ID, but we don't use block ID anywhere, so I is not used. Then in OpenMP, you just create a buffer as a local variable, same as L. And both of them can be shared between threads because OpenMP doesn't say otherwise. It's the CPU model. You can just share every local variable. You can pass the address to your neighboring thread or another thread, and they can write it, read it, do whatever. Again, CUDA disallows this, but OpenMP is fine with it. Then, because there's only one thread running conceptually per team, you have no synchronization and no guarding. There's only one thread. But then to have multiple threads run stuff, you have to introduce an on-parallel. We do an on-parallel for with the block size such that each, like let's assume everything works out. So we have one thread per iteration here, and then J would be the thread ID X, right? At the end of a parallel, there's an implicit barrier, so we don't need to make it explicit. And then roughly the same again here, okay? So this is the OpenMP one. And now you could argue, you know, certain things you have to make explicit there and other things you have to make explicit there. Yeah. I mean, conceptually, as soon as you have an on target, everything that follows inside of that region is executed on the GPU. It has host fallback code. So in case something goes wrong or you at runtime you don't have a device, it would execute on host. So the host code contains a copy of it effectively. But that is everything there goes on the device. And we have to, into the host code, we have to generate not only the fallback, but also runtime calls to, you know, pass all the arguments that we have to determine if it actually worked or if we have to go to the fallback. But yeah, conceptually and everything else, I can't really argue because we have to look at the code. It's a little, you know, iffy. But conceptually, everything after a target is device code. All right. So certain things are explicit here, especially with parallelism. Certain things are explicit there. Okay. Now, in reality, if you write this, but this is not what the compiler generates as code, because I mentioned that maybe before, on a GPU, you cannot share your local variables. Local variables on a GPU are registers. Registers are like local registers. Local registers are only for your thread, not for other threads. On a CPU, local variables that are shared go on the stack. There is no stack on a GPU. There's just registers. Effectively, stack is mapped on registers. And the stack on a CPU is shareable. You can take any thread that can access the stack of any other thread as long as he has an address to it. So this actually doesn't work. So the Clang as a front end has to change those local variables to runtime allocations of a proper size, okay? And then we have to free them at the end and so on and so forth. So that is something Clang does for you because it has to. And then remember, we have the SPMD GPU execution model versus the generic CPU execution model. So we have all of that state machine stuff. Now, what's the first thing what we do? The first thing what we're going to do is we're going to analyze those allocations, those runtime allocations, because these runtime allocations are bad for performance. We actually want the two outcomes that are shown here. For buffer, we want to determine that that is a buffer that is actually shared across the team, right? Every thread in the team might access it. And we want to allocate it in team local memory, in local shared memory, sorry, which is effectively the same thing here. And we are usually able to realize that and effectively get the same allocation as on the CUDA side. You can write it by hand as well. This is not how you write it. This is just because I ran out of space. But you'll see later in the slides how to write it properly. So this is how you use OpenMP to allocate shared local memory. You can do that. That's good. And then we analyzed L, and we realized that L is never shared. It cannot be shared. It's impossible. We prove that. So instead of allocating it, through runtime calls or in shared local memory, we allocate it per thread, which effectively is a register, which is exactly what we wanted to have. So we get rid of this, what we call globalization that happens in Clang for the purpose of making the non-existent GPU stack accessible to other threads potentially. So we get rid of that. Next step is we do SPMization again. So we hoist the parallel out. We've seen that before. In order to do so, we have to guard the sequential code. We have to introduce barriers that were implicit before. We have to make them explicit. And we have to, replace the parallel force that were there with effectively force and barriers. Okay. Yeah. Because I want to make the barrier explicit, because I want to remove it, and it's easier to remove something that I write on the slide than something that I don't write on the slide. But yes, I could just remove the barrier and make a no, wait, it's the same thing. Right. That's why. I mark them as aligned here because we know those barriers are aligned compared to actual OpenMP barriers, which is not what we actually use here. We use aligned barriers. The difference between aligned barriers and an OpenMP barrier is an aligned barrier, we know all the threads will hit it, all the threads in a block in a team. Whereas this a non-aligned barrier, like an OpenMP barrier, might not be hit by all the threads in a block or a team. Big difference because we can only remove the aligned ones for now. Oh yeah, so it's actually not an OMP barrier, it's something else, but it's conceptually, it's an OMP barrier aligned. Oh yeah. And all of this happens in LLVM IR level with runtime calls. Nothing happens on this C level. This is just for me to show it. Okay, so SPMization, that worked great. So now we have all like SPMD mode. We don't have a state machine. Cool. Next step, what do? Is we, wait, how does this work? Oh, why don't I have? Oh, okay. I think I forgot something here. If the user tells us that they provide us with sufficient number of teams, like blocks and threads per team, we can get rid of these loops. If you think about CUDA, you never see these like loops over all the threads in there. The user implicitly says, I'll start it with enough blocks, enough threads. And if I need less or want to guard it, they just do, if thread ID is smaller than whatever the number is I need. But all of those CUDA codes will fail if you provide them with too few threads or blocks. So that is the assumption that CUDA programmers have anyway. And you can tell Clang through command line options to make the same assumption. Effectively, you can tell them that today, it will just not have an effect because that part hasn't been merged. But you can already say it. If you tell that assumption, we can get rid of those loops, which is great because loops have back edges. And if we know that we have enough threads and enough blocks, those back edges are dead. So we would execute the loop body per thread per block only once anyway. So we can get rid of those edges, make the control flow much easier, actually save a couple of registers in the process, which is good. If we really want to go to the same performance, exactly the same performance, exactly the same PDX, it's required. And we're working on making it automatic anyway. Okay.
Could I ask you a question?
Sure.
So you got rid of the distribute up there.
Yes.
Yeah. Can you talk about that a little bit?
I mean, the distribute was only there to to deal with the fact, more or less. I mean, it's not totally true, but for this purpose of this presentation, distribute was there to deal with the fact that we might have less blocks, less teams, than we have iterations of this loop that is distributed. Let's go back one here. So this distribute goes over this grid size loop with a block size stride. If we know we have if we know that we have one team per iteration of that loop, we don't need much logic. if we know we have at least one team for each iteration of that loop, what the distribute will do is it will just give the first team the first iteration, second team second iteration, and so on, until we run out of iterations. And all the other teams will do nothing. And so we can, if we know we have enough teams, we can just say, oh, if your team ID is smaller than the grid size, then you're good.
Okay, good, thanks.
So this is, gets us closer to what you would write in CUDA. Okay, cool. So next step is to eliminate this barrier at the end here because it's fairly trivial. Now that we don't have the back edge anymore, the only thing executed after this barrier is the kernel end. So this barrier is at the end of the kernel. You don't need a barrier at the end of the kernel. There's no code behind it. The barrier is useless. With the back edge, that wasn't that easy because after the barrier could be yet another iteration, right? So this is one of those benefits of eliminating loops and replacing them. Then, if the user actually tells us the number of teams in the thread limit through compile time constants, so I didn't make them constant here, but if those are compile time constants, we can actually get rid of all of the conditionals as well because we can replace those things in the code with the constants. Okay? All right, let's assume the user did because they also, they don't have to, but they can. Let's assume for a second they did. Okay, now we're looking at code that already is pretty much, no, it is the same as the CUDA code. So target teams parallel is just the CUDA kernel launch that we don't see. It's an SPMD kernel launch. The shared is equivalent to allocate in the C group. Allocate in the thread is just a local variable. We do the thread ID check to do the single threaded stuff. We have aligned barriers, which effectively are sync threads. We have all the threads execute this together, again, sync threads. And then this. So we end up with the same code in effectively PTX and performance as CUDA. If you do all these steps, there were quite a few steps, and some of them are not so easy, especially if your program doesn't fit on a slide anymore. Oh yeah, so performance results. Let me. What we see here is XS Bench and RS Bench, which are two proxy apps for the OpenMP app that I mentioned earlier. One is memory bound, one is compute bound. And we started with LLVM 12 as baseline on the far left. And then LLVM def at the time got a speed up of 1.5 to like 13x by doing all these funny things. And the two right bars are actually CUDA. The CUDA implementation of those two benchmarks, proxy apps, one's compiled with Clang, one's compiled with ACC. And you see that while XS Bench doesn't match it yet, RS Bench actually matched the CUDA performance to the T, right? We did more of those. SU3 Bench, we still a factor of 3 off the CUDA performance, but we reduced it by an order of magnitude. Mini QMC doesn't have a CUDA version, so we just got like a 2x speed up there, which is not bad. Okay, cool. What time is it? 15 more minutes. Okay, and then we have a break. I know this is tiresome. All right, cool. Co-designing and optimizations in the portable GPU runtime. So our GPU runtime, the thing that we ship on the GPU with the application, actually runs on NVIDIA GPUs, AMD GPUs, and with a patch that is pending, and we'll talk about later, on the CPU. Why does it run on the CPU? Because we want to debug the code as close as it would look like on the GPU with the same runtime. It's not fast, but the original CPU runtime is much faster. We're not trying to be fast. We're trying to be close to the GPU compilation such that what you see on the host is kind of what you see on the GPU as well, right? Oh, yeah. So how do you get a portable GPU runtime that has all these fancy features and so on and so forth, and is portable across things? While also trying to get rid of complexities in Clang and so on, years long. So we have another longer example. I think I can finish that in the time for the break though. It's already simplified, but this gives you an idea of how the GPU runtime looks. The GPU runtime has some shared state. So each team has some state that they share like across the team. At the beginning of a kernel, we initialize that state. In this example, we only have a single value in that state, that is the team size. So how many threads are currently active in our team? So how many threads are actually executing? And remember, this is conceptually, this is the OpenMP conceptual value. So the ICV that you query if you ask for num threads. Oh yeah, initially it's 1, because this is a generic mode program. So one thread starts executing conceptually, and the other's waiting in a state machine. And then after we finished initializing the state, we have a barrier so that everyone is on the same page what the state looks like, because otherwise it would be bad. And then here's this parallel OMP parallel that basically says, okay, now everyone executes this outlined function together. Oh, sorry, I said this is generic. It's not. This is actually SPMD mode. There's no state machine. SPMD mode, but conceptually we still initialize the team state with 1 because we're at that point not in a parallel region. Then we enter a parallel region. The outline function is this one here. So for all intents and purposes, it just uses the team state. So it calls a function use and it passes the current team size. Okay. Okay. So our parallel function just does use and then get num threads. That's all it did. So this is what we generate. Now, what does this parallel do? Oh yeah, it takes the function pointer and a couple of other things. First thing it does, it checks if we currently have a team of size bigger than 1. What does it mean if the team has size bigger than 1? That means we have encountered a nested parallel region. So the first parallel region increased the team size to bigger than 1. The like if you encounter a nested one, the team size is bigger than 1. What do we do if we encounter a nested parallel region? We will sequentialize it. We'll execute it with the encountering thread. That parallel region is effectively sequentialized. Why? Because otherwise it becomes really complicated. Because you have to map things all over the place. You don't want that. Okay. So first, check team size to make sure we filter out the nested ones. Then we go, barriers all over the place just to make sure that every update and every read from a state is synchronized properly. Then we set the team size properly to the block dimensions. So how many threads do we actually have in our block? That's how many threads we're going to use for the execution. Then we execute the user function. That's the function point that was passed, which is this function over here in the bottom. After that, we reset the team size to 1 because conceptually, again, 1 thread is running. Okay. Oh yeah, optimizations we perform. So this is how the runtime looks conceptually. And what we do is we use interprocedural reachability analysis and the knowledge about the lifetime of shared memory to determine that the only write to team size that could reach this point is the write up there. So we kind of just propagate the value and that conditional falls away. It's dead. So we effectively now realize we're not in a nested parallel region. That's the consequence of it, even though nothing here knows really about, like this optimization that I'm showing you now are not high level, they are low level. They don't know what OpenMP is. They don't know what nested parallel regions mean. They trigger on generic code, including user code, just as fine. Okay, second thing we do is, again, interprocedural reachability, shared memory lifetime, and then we use interprocedural dominance information to say, okay, the only call to this outline function is here. The only, because this write cannot reach this function, but both of those writes can reach this function, right? Effectively, we execute both before we reach this function. But we know that we always like this one, both of them dominate the function, so they have to both execute, and we know the order in which they execute. So we know this one is always the last write. So we can replace the value down here with the value that is written last, right? Dominance helps us here because both dominate. Okay, now you probably realized that we eliminated all the reads from team size. We only write to it. We don't need stuff that is only written. Get rid of it, all of it. Now, once we did that, you realize that we have a lot of barriers that are effectively next to each other. So we have aligned barriers that are next to each other. So all the threads will hit them, and there's no code in between. Those barriers are useless. Let's get rid of those. Once you did that, you're now left over with a call to a function that effectively just calls the function pointer that then has to use blockdemx here. If you inline it and get rid of like the empty abstractions that are now there, you end up with this code effectively, which is what you would have written in CUDA in the first place. So all of these abstractions that the OpenMP runtime has to manage ICVs, like the ICVs are internal control variables, to manage this parallelism, nested parallelism, all of these complex things that have to be managed. We have to deal with them if they occur. We can't just rule them out. I mean, we have assumptions for some of them, but in general, we have to provide implementations for all of these corner cases. And if we use, like we designed the runtime such that we can analyze the code after the fact and determine in high level and in low level what we really need and get rid of all the abstractions that we don't, with the usually effect that we end up very close to what you would have written in CUDA. Oh yeah, last slide before the break. I did talk about these remarks earlier briefly and about assumptions a few times. OpenMP has optimization remarks you can enable with these three command line options: our parse missed, and our parse analysis. The first one are optimization remarks. The second one are remarks about missed optimizations. And the third one are remarks about like analysis results. And OpenMP opt provides all three. And you really, if you're interested in your performance, if you're interested what happened to your program, you really want to enable those and look at them. They are basically one-liners that are associated with a piece of your code, so with like a source location, and that tell you something about that source location. That tell you if we made it SPMD mode from generic mode, if we eliminated the state machine, if we did undo globalization, or if we failed to undo globalization. And so those are really important. If any of the remarks is a bad one, and we'll get to that in a second, that is usually a bad sign for your performance down the line. And then there are those assumptions that are also mentioned as part of the remarks that are emitted, but also on, if you go on the web page, each remark has a web page. Most of them are non-empty. And they have examples and descriptions of what this remark means, why it fires, what to do about it. I mean, at least if it's bad. If it's good, they're like, yeah, we did this cool thing here. We did this to that. And good. So those are all of the assumptions and command line flags that you can use right now. So you can use the OpenMP 5.1 default assumptions, and we sometimes ask you to use them. So the remark says, hey, I couldn't prove the following. Maybe you want to put one of those across like here or for this call or somewhere. We have a couple of ones that are extensions. You are sometimes asked to use them. We use them in a runtime for sure, and they might be useful. So don't put them everywhere. Just put them if you're required to, if you're asked to. There's no point in just blatantly starting to put assumptions everywhere. That's not going to help anyone. And in command line flags, it's probably the easiest way to get performance or to break your program. If you violate the assumptions you give to us, you're on your own. If you don't violate them, your performance is probably going to be better. And we have CUDA mode, which effectively says, it's the old name, this is why we kept it. It effectively says, I'm not going to share local variables with my other threads, I swear. So it basically gives you CUDA sharing semantics of local variables. So we don't have to do globalization. And if we don't have to do globalization, we don't have to undo globalization, which is good, because that sometimes fails. No nested parallelism is, pinky swear will not nest parallel regions. Sometimes we fail to determine if that nesting may or may not happen. And if we have to account for it potentially happen, we have to generate extra code. Extra code is costly. No thread state is, I will not change an ICV value while I am in a parallel region. Why is that a problem? If you're outside of a parallel region, there's conceptually one thread. If you change an ICV value, for example, you set max num threads or you do something else, what will happen is you effectively change that for all of the threads because there's only one conceptually. But if you now have a lot of threads that are in existence and one of them changes an ICV value, we have to start tracking that separately. We have to track for the rest and for that one. And tracking stuff separately requires more code, and we've been there. It's costly. So no thread state is a big one. And those two are the ones that I described earlier to get rid of the loop. I promise you, I will give you enough teams and enough threads to execute the iterations of the distribute and parallels, the for loops, without having the back edge, but they don't work yet. I mean, you can provide them, but they don't do anything. And nowadays, we even have one environment variable assumption that you can set. That is, if you read the standard says a map clause, if you map memory to or from the device, has to be atomic. Yeah. Mapping stuff involves copying things. That's not that atomic as you might hope it is. So it takes time. So if we want to make the impression it's atomic, we actually have to, deal with, we have to synchronize things, we have to lock things, we have to, do a lot of work to make it appear atomic to you. But for the longest time, we actually didn't do that. It was just broken. I mean, we didn't get to implementing it yet. And most applications run just fine. So most applications don't need this. I can show you how to trigger it, that you need it, like that. And we have enabled it by default. So you now pay for something you probably don't need. You can disable it and then you don't have to pay for it anymore. Okay, make sense? Okay. Some runtime results, but at the end of the day, XS Bench, if you remember, that was the one that was not quite there for CUDA performance earlier. We're now really close. This is CUDA. Yeah, this is CUDA, and this is us with the new runtime that we developed with optimizations that I showed. So basically, I mean, there's still a difference, but not much. And on the RS Bench, which was already CUDA performance, we still get that. And test snap, 50% improvement, and mini FFM, still not CUDA, but 80% improvement. So we're good. Okay, let's break. First things first, I put a link here on the slides, which you obviously, you don't have to type it. I'll share the slides after. This link goes to a study for OpenMP developers that is probably very important and very great. So it would be great if we could both take the study and distribute the link. There will be more information about it, probably included in the slides after. But I just wanted to, mention to everyone that there is this thing, and we should, participate and distribute it. And more information on that can be put in the chat as well. Are you logged into the Zoom session? I mean, it's one way. Otherwise, we'll put all the information on the slides afterwards. Either way works. And then we'll share the slides so people can actually, click links because I have a lot of them. Okay. And then we're going to continue. Again, if people have questions, comments, concerns in between, please, stop me. You don't have to go through this as I put it in this order, because not everything I had a reason I put it in the order it is. A lot of it just ended up where it ended up. Let's take a look at memory allocators. So the standard supports a couple of memory allocators. that allow you to say where you, like, from what kind of memory you want to allocate. And in the GPU land, kind of where, like, we interpret that so far mostly as in which kind of GPU memory do you want this thing to live. There is the default ones, and there is more than what I have here. And then there is extensions that we have in LLVM that are now, I think, already voted into the standard or not, but I mean, they transition to be proper standardized allocator places. And then you can write something like this with a buffer, as we've seen before. In CUDA, you would write __share to create a buffer in local shared memory. That's kind of a very important concept to, do fast communication between threads in a team. To do that in OpenMP, you would do this OpenMP C group memalloc here. And then if you have some memory that is globalized, like some variables that are globalized, but they shouldn't be, but the compiler is unable to figure out, one way of dealing with this is to just tell the compiler that you want to allocate them in thread local memory. And then we know we don't globalize this. It just goes into a register. Okay, the extensions for GPU memory are basically what you know from CUDA, just mirrored into OpenMP land. Host memory is, let's start. Device memalloc is just a regular allocate me global memory on the device. Shared mem is allocate me memory that can migrate. That's the idea. So memory that can be accessed from host and device. Preferably it migrates by page rather than you have accesses all over the place. And host mem is pin memory effectively on the host, which now allows, like, you want to have that for two reasons. One is, depending on your system, you can actually access that from the device code directly, which is not cheap, but you can. The other reason is if you use that in a memory copy, you probably get faster copies and, more importantly, asynchronous copies, rather than what happens if you use non-pin memory in a copy to GPU or back. It will usually copy into a pin buffer and then perform another copy on the host. So you avoid that overhead if you use pin memory to begin with. We even have an experimental patch that would allow you that would tell the runtime to pin all the memory that is ever involved in copies between host and device. So it would, whenever you do a map, it would automatically pin that memory, which can actually improve your performance quite a bit without you having to touch anything, because it will just do it for you. It can also backfire. So I don't think it's merged, but it's out there. So if you want to try that out for an app, that's actually an option. Okay, and an example here.
Johannes.
Yes.
The page before that page, you went over too fast. One more page back. Could you just do this page again? C group, P team, and thread. Those allocators.
Okay. I mean, now you called me out on something I tried to avoid to speak about. So thank you, Greg. So on thread mem is, let's start from the bottom because that is the easiest. On thread mem is you get you allocate for one thread. You allocate in thread local memory, which effectively will be a register. P team in C group. Now, conceptually, what you should use to get shared local memory, like to get memory that is shared across a team, is the P team memory. But for an historical accident, LLVM uses C group. LLVM doesn't do anything with P team as of right now, but it could. It could also use that for shared local memory. We get away with using C group because right now it doesn't make a difference given the way we implement things. As we evolve, we might, like, it's probably would be wise if we transition over and start to, tell people to transition over. But right now, we use C group where we should have used P team, and we don't do anything with P team, but we should. And C group is okay for now. C group means contention group, whereas P team is, your team. But again, I actually hope not to speak about this because this is.
No, that's okay. I get the confusion. Yeah.
Johannes, another. Can you hear me?
Yes.
In the second allocate, do you mean flag instead of buffer?
Okay, I could hear you in the beginning, but then it was kind of hard.
Sorry. I said in the second allocate, do you mean flag instead of buffer?
Oh yes, sorry. That was supposed to be flag rather than buffer. Yes.
So the one I'm missing when I'm inside. So cool. These are cool because they're inside the target region. The one that I keep looking for is when I want a variable to be global, a global memory, like not shared and not thread local.
Yeah.
Right. I think by default, you get pretty much thread local on flag there, for example, into flag. But
if you want a global variable, I mean, just put it into global space. I'm not sure. It's like allocating stuff in global memory is the easiest.
Right.
Kind of, everything else.
Still stuck at how to do it.
I mean, you move the in flag into, for example, just out of the function and like make it a global, and then it lives in global memory.
I mean, A is global, right? In this case.
We don't know. Nobody said that.
But okay. But so, I mean, I can see how to get global from outside the target region, right? But when I'm inside, if I want to just do a local variable that I want to be global, that's where I'm stuck. Okay. But I don't want to hang you up too much on this, but that's kind of,
if you want a local variable inside of global space, make the flag static.
Okay. All right.
Static flag will give you a global, like it will basically go into global memory as it would on the host. So it's not local to the thread anymore because it's a static, but so that way you could deal with it. Or you make it a global variable in the first place, like by actually putting it, outside of a function and make a declare target to make it available on the device.
Right. And I'm just giving you the use case of that is where I've got something I want to share between work groups, between teams.
Yes.
And atomically access it. I want to atomically access that thing.
Yeah.
That's what I mean.
Both ways work, yes. I mean, both ways that I described would work, or you pre-allocate with like the allocator routines on device alloc and so on.
I got it. Good. All right. Thanks.
Right. On alloc, and here, like the example for shared memory, that is effectively what CUDA calls managed. At least that is what we kind of want with that. And then you don't have to map it yourself. You don't have to map it between host and device. It just migrates. That's the idea. Okay. Now, OpenMP has, CUDA and HIP have this concept of dynamic shared memory. So when you start a kernel, you can tell the kernel launch how much shared memory you want to have. And you access that by creating a global variable or global declaration that is just in __ shared some pointer. So that pointer will point to the dynamically allocated shared memory. And you can determine how much you want at kernel launch time. So basically, you can create a buffer of variable size at launch time, because __ shared only works with constant sized otherwise. So that is the way to get around and get actually dynamic sized buffers. OpenMP doesn't have that. It's bad, because if you want to move a CUDA code that uses it to OpenMP, you are left with no good options. I mean, there's a lot of options you can go, but none is great. So we introduced a partial support for this. I mean, effectively, it is support for this, but it's not perfect yet. You can use this function here, LLVM target dynamic shared alloc, to get a pointer to the dynamic allocated shared memory that you can use to share values between threads in a team. Same as with __ shared on CUDA. The problem is we currently do not support to determine the size per kernel invocation, per target region. All we can do right now is you give us an environment variable with its size, and every kernel launch will get that much shared memory, like dynamic shared memory. We'll get to it eventually, and then you will. The thing is, there is no existing flag like clause for it, so we have to make one up, and then we want to propose it to the standard, and so on and so forth. But generally speaking, this allows you to, at least for now, emulate this feature, even though it's not a perfect rule, but we're getting there. Back to optimization remarks. We talked about this earlier. Our path for successful optimization, our path analysis for things that analysis tried, or like extra information that you might want to see, missed, and then there is not only, you can use it with OpenMP opt, so you get remarks from the OpenMP opt path, but you can also get remarks from other passes. Vectorizer is one of them that has reasonably good remarks. And the OpenMP remarks look like this. They end like this. Sorry, that's what I tried to say. So they end with an brackets, omp, and a number. Each remark has a number, so you can identify it. And then you can basically also filter and say, oh, what remarks did I get? Oh, I got a lot of 110s, and I got a few 112s, and one 212. So, and then you can go online and look up what these mean. If you're looking at remarks, especially not the OpenMP ones, but potentially there as well, it might be interesting to use profile-guided information to filter remarks that are hot. So filter remarks that are in code that is actually executed a lot. Because, I mean, if you have a large application, there's a lot of code. Most of it is irrelevant, or depending on how your profile looks, but it could. And if that is the case, you really don't want to see 10,000 remarks. You want to see the 5 that are the most important. So LLVM allows you to generate profile information for programs. Right now, only on the host, not on GPU. And then it allows you to use those profile information to either do better optimizations, which is then called PGO, profile guided optimizations, which is good. You should do that. People do that if they really care about performance, and it helps. And it also allows you to identify or to filter remarks, to only show remarks that have certain criteria that are like a certain hotness and so on and so forth. Oh yeah, so if you turn on these remarks, you put in some code, and then you get these remarks that tell you, hey, by the way, this loop was not vectorized, cannot prove it's safe to reorder floating point operations. Floating point operations are not commutative and associative. So you can, it actually tells you a little bit more what you can do about it. One way of enabling vectorization is to do on SIMD, which effectively tells the compiler, pretend this is vectorizable, like pretend floating point operations are commutative, and then you're good. So this is kind of the workflow you should adapt if you're on the tuning part. And then for OpenMP offloading, same idea. And then here we have a local variable again, and the local variable, the address of the local variable is taken and put into some outside function. So now we don't know if that local variable is accessed by other threads, so we have to globalize it. So that is possible. And given if this is all we see as a compiler on the left side, we can't undo globalization. This is not enough information to undo it. So we emit a remark and say, okay, we have this globalized variable that we found. It's potentially captured in this call. And if it's captured, it could like the address of that local variable could be given to other threads. And at that point, if it's not captured, you can use this attribute no escape. And then online, you can also look up OMP113. So if you put in attribute no escape, you tell the compiler, this function will not capture this pointer. And capturing effectively means it will not make a copy of the pointer that outlives the function. We use it in a weird way, but that is what it's supposed to be. This is how the web page looks if you go online. OpenMP.LLVM.org. OpenMP.LLVM.org, yeah. And then there is a menu and it says optimization remarks, and you land here. And it tells you how to enable them, and it tells you other stuff about them, how to save them to files, how to show them in line with your code in like a source viewer, other stuff. And it shows you what optimization remarks we have, a very short description of them, what diagnostic kind, like what remark you have to enable, just remarks, remark analysis, remark missed, and a link to a page that explains them better. And most of them should not be empty. Some of them are just empty pages. Oh yeah, completely change of topic. Device functions, device math functions especially. Anyone here ever looked into how GPU languages deal with host library functions? It's very good for you. I envy you all. It's messy. The part that works, and most parts don't. So the only part that really kind of works are a couple of predefined ones like malloc, printf, and free. Those are, they made them work because they're too important and people could really not go without. And maybe a search or so. And then math functions, because kind of math is like still one of the drivers for GPU computation. So how do math functions work in Clang for CUDA, HIP, SYCL, OpenCL, OpenMP? It doesn't actually matter what you do, any offload kind of thing. And I say in Clang, most other compilers do the same or something similar. There are exceptions though. So if you're interested, we can talk about it later. But generally speaking, what happens is, in contrast, so the underlying issue is you do not have the host libraries on the device. There is no libm on the device. There is no libc on the device. You just don't, like, they are not there. So if you see a sign call and you go into your system headers for math, you can look up how that is implemented. And the funny thing is, if we have 8 people here, you probably will find 8 different implementations depending on what Linux you run, what other like operating system you run, and so on and so forth. Everyone does it differently. It depends on the target architecture. If you have an ARM computer or an x86, it's like a mess. It's the Wild West. The only thing we really agree on is the fact that there is a sign and it takes a double, and it returns a double. That's it. And after that, everyone for themselves. So how we deal with the fact that we don't actually, that the host is so diverse and nothing really, you can't make any assumptions about it, but because they will fail for sure. So how do we deal with this is Clang provides implementation for all the math functions right away. So Clang will introduce a header file into your application, if you want it or not, that will define sign for the device. And it will define it as a call to whatever your target architecture provides as an implementation for sine. Like in NVIDIA, it's __NV sine. So the client will include a header that will basically say, oh, double sine double is just going to return the result of passing that argument to __NV sine. And then we're going to say, oh, and there is a function __NV sine, which we don't define. It comes with the vendor provided device runtime, lib device that is part of your CUDA installation. Okay, so that's roughly how it's done, right? Now you might wonder how that works because there is already a sign on the host, and you also include that because there's a header and you potentially have a definition there. But we'll skip over that. If you're interested, I can explain that to you. But it ain't pretty either. So now the problem with that approach has been and is that LLVM knows about sine. LLVM knows that sine is a function that does math. It will not read any global memory. It may write ANO, like the whatever ANO is, which is also an interesting question, but I'm not going to answer that. So it might write some global memory, but it will not read any global memory, and it has other properties that we know of. Sine is actually kind of a nice function. But LLVM has no idea about __NV sine. Now, you could argue, oh, we could just teach it the same things about __NV sine, but I'm not like starting to list things. It doesn't matter in standards or in compilers or in other parts of software is usually a bad idea. There's very few reasons to do so, so you really don't want to. So we don't do that. What we really want is we want to keep the sine call alive and allow the compiler to treat it as a sine, and only in the end replace it with the vendor provided implementation. But we actually have to implement it with the vendor provided implementation and to run a few optimizations, because otherwise we might lose out on performance. So we kind of want to run optimizations while it is sine, and we want to run optimization while it is NV sine. And that is where link time optimizations come in. So what we ended up doing is we effectively created a device math library. So we have a libm, effectively, that contains the implementation of a lot of the math functions for your GPUs, for all sorts of GPUs. So we have a static library that contains them for all your different sub-architectures of your AMD and NVIDIA cards. And then if you run your program now, that is not upstream, but will be upstream soon. So, and if you then compile, you'll actually keep the sine thing. You will get the optimizations with sine. And then once that is done, and at link time, when everything else is linked together, we link in libm. Grab the implementation for the device, link it in with your application, and run another set of optimizations there. And that way you get the best of both worlds. You get like knowledge about what is going on in the math, plus optimized vendor implementations. That's kind of important. So just wanted to mention that. Yeah. I mean, the easiest is you want to inline that call. You actually don't want to have, usually you don't want to have calls. So you want to inline that call. But the thing is, we also know the implementation of NV sine at that point. So we can also inline the NV sine call. And then we can also simplify the implementation of NV sine based on the arguments. That's why you want to do the optimization. So you can get rid of 2 levels of calls and specialize the NV sine for whatever the argument is at that point. And some of those, I mean, it's not only sine, it's like all of them. And some of them have, fairly obvious opportunities to specialize. A lot of these math functions start with, oh, is the argument none, or like not a number, or is the argument, some infinite, or is the argument positive or negative? And as long as we know something about the argument, we might be able to, get rid of a lot of code that we otherwise would have to at least keep, which is already there. So, cool. Okay. I'm going to talk a little bit about a driver and a linker. There is going to be a talk about that, a paper at IWAM on Thursday. So I'm actually not going to talk too much. The paper is about the just-in-time compilation and link time optimization. So they will. I'll go over some stuff here, but questions and more stuff is coming there. Okay. I'll also not talk about just-in-time compilation at all. Okay. So this is how we do the offload compilation nowadays. Compilation at compile time and at link time. Compile time, we have our input source code. We split it up into host source and device source. Then we run device. So we use the host source for the device compilation. Then we create object files for both. So if we do non-LTO, so we create object files for both, and we embed the device object into the host object. And then at link time, we kind of undo the embedding. I mean, we did the embedding, so we have a single output file, even though we compile for multiple architectures. So we undo the embedding, and we link in, libom target and other things. We put it all together. How does this? Yeah. So how is this actually handled? So active tool chains are all of the devices and sub-targets that you enable. So you can compile for like SM80 and GFX 908 at the same time. So you have two active tool chains. One is an NVIDIA SM80, and the other one is an AMD GCN GFX 908, which is like an A100 and an MI100. So for each of them, we create a device object. Then we pack that in the host object, and we pack that into some funny global variable, which is just a binary, a binary blob, a lot of bytes in a specific section of offloading. That way we find it later. So we basically use section names to pack things in the right place. We have one section that describes all of the kernels and global variables that have to be registered with the runtime. Because the runtime needs to know about certain global variables. It needs to know about what kernels are available and so on and so forth. So we have a section that lists them effectively. And at the start of your application, if OpenMP offloading is enabled, we have a constructor, a startup function that runs before your code runs. Like the code that initializes global variables runs before your code runs, right? So we have that thing that will look inside of that section, go through all the kernels, go through all the global variables, and register them with the runtime, so the runtime knows what's going on. In the LLVM offloading section is each of these device images. So we have some metadata that says, okay, what is the target triple? What is the sub-architecture? So we kind of keep track of things. Then the binary blob of the actual stuff, and some stuff in the end that I don't even know what it is. Okay, and then if we do LTO, what we can do is what we actually embed into the host object file. So device LTO and host LTO are separate. So if we do device LTO, what we embed into the host object file is LLVM IR, effectively. So when we get the linker, gets all its object files, extracts the device, extracts the device bitcode files, and links them all together into a device object. And we use the vendor tools to create the final result, like QBin file or whatever the AMD equivalent is called. And then we wrap it again into the final executable. So at link time, we either link together device objects through vendor tools, or we do LTO, do code gen, and then link it in. Okay. As I mentioned earlier briefly, you can now embed code for multiple architectures, which is new, works now. So you can compile a certain piece of code for multiple devices, sub-devices, or completely different architectures if you want. Here's an example where we compile it for MVPTX SM80 and GFX 908. And then you can take a look at the object file that we generate, and it has this .LLVM offloading region and the offloading entries, as I showed before. One of them just determines all the kernels. The other one contains all the blobs of memory inside. You can actually also ask it to tell you more about what is contained in there. So you can use the LLVM object dump with the offloading flag to get information about the embedded device code inside of an object file. You probably won't need this, but if you ever need this, this is really handy. Because if you really need this and something like this is not available, you have a problem. So LTO, right now you have to actually pass foffload LTO also to the link step, not only the compile step, which is a little unorthodox, but it is what it is. And we talked about that before. And LTO is good. I would enable it if I were you all the time. These are some results about LTO compared to ahead of time compilation. And I mean, if these benchmarks here, up until here at least, do not require, like they have a single translation unit. The code is not split across translation units, but you still can get much like benefits, 30% improvement, even if it's a single translation unit, just because we effectively run more optimizations. And sometimes you get the benefits because we can do the math optimizations now. I think this case was actually the math optimizations. We could hoist a math call out of a loop because we have this, math library stuff with the split, and then we optimize it later. So this was actually helpful. GPUs are very, we have heuristics everywhere. Compilers optimize, but they optimize according to an abstract optimization function that somebody made up. It goes wrong sometimes. I don't know why we slow down, but that's my explanation to this. So we made a wrong choice. We inlight too much. We unrolled the loop too much, something like that, and things go bad. But go back to, these are applications that actually split across multiple translation units, and you can see that there's important. And this is the one where we used Unity build, CMake Unity builds before. Poor man's LTO. We don't need that anymore. We can use device LTO. The real benefit of this is poor man's LTO also effectively enables monolithic LTO on the host. And you might not need that. And if you have a lot of code, that will cause your compile time to skyrocket. So the CMake Unity build was way more expensive compile time wise, but we get the same device performance if we just enable device side LTO, and we save a lot of compile time. So that is kind of why this is important. Otherwise, the CMake Unity build would have been fine. Oh yeah, I mentioned that before. Static libraries are now supported. So when you build static libraries with device code embedded, it should just work. We should be able to pull out only the device code we need. So if you build a static library that you ship to people, you can include all the different sub-architectures that you want. And we effectively do that nowadays with our device runtime. We build this one static library that has 64 different sub-architectures embedded. And then we pull that in, and the linker will pull out the sub-architectures it needs for the actual application, depending on what the application specifies. One more thing is, as you see here, you don't actually have to specify the entire target triple anymore. The simplified notation now works. You can just say offload architecture, offload arc, and you specify the sub-architecture, which is the kind of important part. We guess the rest, and we usually do a good job at guessing. So you don't have if you go back here, let's go really back. I don't have a good example of where it's the really long thing. It was So you used to say f OpenMP targets equals MVPTX, and then you said something like minus x OpenMP targets minus marc equals to SM80. So it was like a mouthful. And all of that is supposed to now be just offload arc equals to SM80. Right. So you can also generate device-only libraries now. So you can build a static library that actually doesn't have any host code. You can do it like this. There's different ways of doing it. This is one way. It's actually kind of cute. That's also how we do it. You can use this new driver that I introduced earlier that we use that has all these super duper features. Now for CUDA and HIP as well, but they are still opt-in, so you have to specify you want to use the new driver. And then it allows you to do some, like, for example, the RDC for CUDA that Clang wasn't supporting before, which effectively means that which effectively allows LTO in the first place. Let's not get anything. Okay, what is this about? Oh, yeah, you'll hear about this later. Okay, and this is kind of a fun thing. Now you can have CUDA code and HIP code and mix it with OpenMP offloading code. But you should put it in different translation units. So you can use OpenMP CPU code in a CUDA file. That should work fine. But mixing offloading code in one file is probably not going to work. I have no intentions of supporting that anytime soon. So if you just enable device LTO, it doesn't matter if you have it in the same file anyway. So why would I bother trying to make that work? So here you can compile the CUDA file in CUDA mode. It has CUDA semantics. You compile the OpenMP offload file in OpenMP offload mode, and then you link them together. And then you can call both functions in your either CUDA, from either your CUDA kernel or your OpenMP kernel. There is a caveat to it. Global state doesn't translate. Unclear if we could ever handle that properly. You can pass state between, but not like global state, like global variables. That's iffy. Here. Oh yeah, in case you only want to emit the device code for something, like one architecture at a time, you can use this flag. This is mostly interesting if you want to inspect what it generated. The alternative to inspect what was generated is to use -- save temps. Great flag, you really want to know about it. Save temps stores all the temporary files that were implicitly or explicitly generated by the compiler into actual files on your hard drive. So you can look at them. You see, what did the preprocessor do with my input? What did the Clang generate in LLVM IR before any of the optimization? Really, what did Clang generate? What was the output of the assembler? What was, and so on and so forth. And especially if you have like LTO things, you also get the intermediate files like the IR of each translation unit, the IR after we linked everything together and linked it to runtime libraries and so on. So you see all of the steps and you can actually inspect what was going on in a much nicer way. But offload device only is sometimes sufficient to circumvent. And then in case I mentioned earlier, we have for all target regions, we have host fallback code. Sometimes you do not care about host fallback code, or sometimes it might actually be problematic. For example, if you call inside your target region, you call a function that only exists on the device. Let's say you call a CUDA function, and you only have the device version of it. Now, you can deal with it in various ways. You can provide a host version that does nothing, or that does throw an error. But that is also, somewhat cumbersome because now you have to define like functions for no good reason. And most of the time, if you have something like device, like you really only want to run it on a device. If it doesn't run on the device, it's pointless. So you can say offload mandatory as a compile time flag, which will prevent us from generating host fallback code in the first place. If you use OpenMP parallel inside of your region, yes, it will be. Right, and this will disable host fallback code together. It's really useful if you have device-only code. Oh yeah, you can pass things to the linker wrapper, which is the thing that invokes the device toolchain to pass things to the device toolchain, like extra flags for PTXAS and so on and so forth. Okay, that was my quick intro into the driver and linker. As I said, there will be a talk on it, and there will be more like experts here that you can ask about it. So I'm more interested in this part, but questions about the last things that we heard? No? Cool. Then we're going to look beyond standard OpenMP. We're going to look at the things that, at least for now, are researchy, but fun. And then they're moving into they're moving into production, at least some of them as we speak. Okay. I mentioned this a couple of times before. You have offloading, and the tool chain for offloading looks completely different than the tool chain it looks on the host. Now, if you are starting to debug your stuff in offloading, one of the problems is that the tools to debug, like GDB, are not as mature on the device as they are on the host. The vendors have their extensions and so on and so forth, but they're not as mature. The host is still the gold standard. The host is the easiest, always been. So what if we could emulate a GPU on the host and run it there? We could reuse the entire, actual offloading toolchain. We could use the same compilation. We could use the same runtime, but we could run it on the host, which allows us to analyze problems with the runtime, with the toolchain, analyze problems with the device, and so on and so forth. So we built this virtual GPU, which is to offload to. If you think about offloading, this is how we did. This is roughly how the compile part works. We have the input. We split it into host and device compilation. We link in the device runtime. We embed there in a host object. And then at runtime, we use libOMP for the host part and libOMP target for the offloading part. libOMP target is going to use plugins, one plugin per architecture, like a CUDA plugin, an AMD plugin, and so on and so forth. And those are going to open the vendor SDKs, so the actual CUDA SDK, because that is how we communicate. If we do virtual GPU, you don't have that. There's no, we made that target up. So this is roughly how our virtual GPU looks in like a nutshell. It is, it has multiple CTAs, and all the numbers can be defined at runtime through environment variables. So it has, here 2 CTAs, which are concurrent units on which you can run a team or a block. Then it has multiple warps, here 2 warps per CTA, and then it has multiple threads per warp too. Technically, you can pick any number, but it's usually better to make sure the threads match to threads on the host. That makes things easier. And then we have to go outside of OpenMP to implement this for various reasons. So we use C++ standard threads for this that actually emulate our CPU threads. But now, right. So each thread has access to these different environments. Each thread has its own thread environment, but the threads in the warp share a warp environment. The warps in a CTA share a CTA environment, and all of them share the virtual GPU. So think of it as a tree. We have to really use non-OpenMP means to organize these threads. It's like the barrier from C+20. Currently, we don't really do much smart stuff with regard to scheduling. GPU-specific things like shuffles, where you move data from one thread, like a register in one thread, to a register in a different thread, are implemented through explicit schemes that take a value, put it into like a shuffle buffer, like a temporary buffer, we bury it, we move it out, we bury it. So it's like everything is a little expensive, but we really try to emulate the same model and we use the same runtime. So we actually didn't change the runtime implementation. We just implement all the native GPU functions that the vendors provide us with through alternatives of the host. And everything can be configured through runtime variables. Okay, so this is roughly how the implementation looks. So inside of our device runtime, we have all sorts of functions like get thread ID in block, which returns what hardware thread ID am I in my block. And usually that would just call it a built-in function or an intrinsic of the underlying language, like thread ID.x in CUDA, whatever that resolves to, this would resolve to. But then we say, okay, if you compile this for the CPU, if you compile the device runtime for the CPU, use this implementation instead. So our device runtime is implemented a lot with declare variants. So we have the device runtime is a lot of generic code. That generic code calls functions that are then specialized per architecture through declare variant. So the declare variant says, oh, if you compile for something that matches here, the device you compiled for is the CPU, use this implementation. So that is how we kind of do single source code base, but we can compile it for all kinds of architectures. And then the implementation is always roughly the same. Get the appropriate environment and read the value out. And in the environment store values for each thread, so on and so forth. And the thread environment is per thread, so it's thread local. There's other things that we have to deal with. For example, shared memory on the device. The hardware will automatically duplicate this for each team. Each team has a copy of that memory, right? On the host, ain't such a thing. So if you have multiple teams, you have to deal with it yourself. Otherwise, they all share one copy, which isn't the same as sharing different copies. So you go and we just explode the memory into a maximum number of teams that we support, and then we access the proper element, and so on and so forth. And then to run this, you effectively target your host architecture with, and here it's like a little tricky. We implemented this as a vendor. Target triples that determine what is the architecture you're targeting, contain different parts, architecture, sub-architecture, implementer, and vendor. And in order to make our lives easier, we just overloaded the vendor part, which is never, like you guys would have not used it anyway, so it doesn't matter. So the vendor is OpenMP vGPU. So you pick your current, like your target host architecture, whatever your host is, you say, oh, and the vendor is OpenMP vGPU. We're like, I know what you're doing here. Because if you don't do the vendor thing, you're actually offloading to the host, and we're going to use the host runtimes, the host compilation, and we're going to basically trying to make it fast, right? You're actually offloading to the host. Okay, why would you do all of this? I mean, one thing is you can run it, you can just attach GDB to it, like you would have done with any host application, and you can get crash reports on the host rather than hope that your GPU debugger is not going to crash itself. You can also do breakpoints and so on and so forth. You can run Valgrind or any other tool that just works on the host and is ready to be used on that executable, and you're good, right? All of that is kind of nice. Okay, now a couple of smaller things. Device info is a executable that you distribute with LLVM. So if you build LLVM or you get a distributed version, it's an executable that exists in the a bin folder. It's called LLVM minus device minus info. If you run it on a machine, it will tell you what we detect as devices there. So what GPUs and other devices we detect, we can actually because it helps you to get an idea if that is a problem that we actually couldn't detect the GPUs properly and so on and so forth. It also tells you all sorts of things about devices. Think about the CUDA SMI tool, but it's portable as we are everything portable, right? So this gives you information about the device and what devices we have. Plus, the numbering should be stable, so you will get an idea of what number we assign to what device. Target profiling, I mentioned that earlier. You can use libmemory target profile, the environment variable, to tell the runtime to profile all your offloading tasks, like moving data, starting kernels, how long did kernels take, and so on and so forth. And it will create a Chrome tracing format with source line information if you enable source, like if you compile with source line information, like -G or -G line tables. And then you can, inside of Chrome or another tool that reads Chrome traces, you can then see where did I spend my time, what target region, what update function, what data region, with all the nice things that there exist. We're currently working on actual kernel profiling, like profiling what parts of the kernel took how long, and allowing you to do kernel profiling, to basically say, oh, start profiling region XYZ here, stop profiling region XYZ there, and put it into the same graph of everything else in a portable way. And we would ship that. I mean, this is kind of, let's call it the poor man's alternative to these high-end profiler tools that you find, like, the, what are they called? ScoreP and all the others that I don't remember. So if you have access to those and they're set up and you can just run them, cool, go for it. They probably know way more. But this is, the low-end solution that will just run on your laptop as it is. You install LLVM and this is available. That's it. Oh. Okay, fair. Yeah, that's certainly a fair point. We should have some way of saying, okay, I mean, I would probably see an environment variable flag that gives you like a regex, like you put in a regex and say, only functions that match or only regions that match this regex, put them in the profile, everything else ignore. Yeah, that makes sense. I'll take that back to, the people that do actual work. Yeah, keep the suggestions coming, and also afterwards. I mean, we're looking for people to try things out, coming up with suggestions. Some of this is developed, into the blue. Some of it comes from people coming to us and say, "Hey, we have these problems," and so on. Some of it comes from we have the problems, so we try to come up with solutions. Okay, this is a fun project. I still find this is a fun project. So OpenMP classically was, you have your host, you have your intra node saying your CPU stuff. And then we added these GPUs, and now you have like the GPUs. Once you sit back and realize that OpenMP, everyone associates OpenMP with shared memory, like not the GPU shared memory, but like a shared memory system. All the threads can access all the memory, right? But we actually broke with that when we introduced Target. If you don't enable unified shared memory, you move your memory explicitly. You say what goes where, you move it back, you update it. You're in charge. There's no unified shared memory is not on by default. So it's actually a kind of non-shared memory, distributed memory system at that point that you're programming, right?
But there's a sense there. The document says weakly consistent. So that's a relative thing. So it's consistent at the boundaries of the target region and that's pretty weak. I'm talking non-unified shared memory mode. So it's not like you broke with it. It's just that it's with GPUs, you're more weakly consistent. You're more weak, right? You're only consistent at the boundaries of the target region. Does that make sense?
Yes, but you still have to declare memory and move memory yourself. You have to still say this variable has to also exist on the device. Otherwise, accessing it will fail. When you have to move memory, otherwise, and update memory, otherwise, you'll read stale copies.
No doubt. But that's why I think we have this word map instead of copying. The mapping means that the copying will be done. Yeah, I agree with you. We're in agreement, but I still think, without the unified shared memory, there's this notion that the variables are virtually there. Of course, they're not the same memory in a discrete GPU, but from a modeling perspective, that's the goal, right? With the map clauses in a discrete GPU.
What you're saying, but not even all variables have to be on both sides. You can make variables that only exist on one side. You can even target them with an update. It's possible.
Yeah, I got it. Yeah. But that's
the point is, we already kind of did take over that memory management task with the GPUs. Okay. Now, you can program one GPU and two GPUs. So we also allowed multi GPUs. So we have like different devices, and then we have different device numbers. Okay. Now, how do you know that your GPU to which you move the memory and the compute is in your machine? You don't. Before, it was kind of a kind of fair assumption with the CPUs and the parallel threads because, I didn't have to move anything. I mean, it was just, it could have been a different machine, and people made these approaches where they had distributed shared memory machines and so on and so forth. But here we already move stuff. At that point, what's the difference if I move it locally to like a GPU or to a GPU that is in the cloud, right? The code is exactly the same. And that's what we kind of realized. So we took an application and we made it multi-GPU in the first place because otherwise it's kind of pointless. It's more interesting if you have multi-GPU. And then you can execute this on all your local GPUs, which are on a high-end server Watt 8, roughly what you can get. But who says to stop there? So we basically exposed the other like GPUs in other servers in Google Cloud or in like nodes in a cluster to the program as if they were local. So if you ask, hey, get num devices, the answer was 150. And they were all GPUs. They were obviously not local, but from the perspective of the user, it doesn't make really much of a difference. There's a performance penalty to be paid, but other than that, programming-wise, it just works. Same code, no change whatsoever. And then you can run it from, 8 GPUs on one node locally to 120 GPUs in 15 nodes in an cluster. And you can see that you now need twice the amount of time for this XS benchmark. So you pay by doing this, but you also get 150 times as many GPUs as you had or in this case, 15 times as many GPUs as you had in one node. So it's and you didn't do anything to your program; it just works. It's all behind the scenes, so it's actually kind of neat. Sure, you can also S3. So there is on the OpenMP LLVM.org, there is documentation on how to set it up. And you can, if it doesn't work, you can reach out. It's the idea is as follows. So I talked earlier, and I have a graphic somewhere, but I'm not sure if let me see if I have it in my slide deck, because if I do, I can show you what the graphic. Lucky me. So, source code, sorry, application, right? This is the application at runtime. It talks to libmom target, which is a target agnostic runtime that we provide that deals with all the OpenMP semantics. Reference counting, keeping track of what kernels they exist, where data is, stuff like that. That libmom target talks to the plugins. Those are one per architecture. In this case, the CUDA plugin. The CUDA plugin will then eventually talk to the CUDA runtime. It can or cannot, we don't really care. And then that talks to the device. libcuda RT is effectively our driver, driver that talks to the device. So what we did is we put in a new plugin. The plugin implements basically the same interface. Here, number 2 is like what the interface looks like. This plugin is called RPC Client, and it effectively implements the same interface as the other plugins. So to LibOhm Target, it looks the same. LibOhm Target cannot tell the difference between what the CUDA plugin, like for LibOhm Target, the CUDA plugin, the AMD plugin, and this RPC plugin are all the same. It knows it's at different plugins, but doesn't know the difference. Like other than that, doesn't know the difference between them. It interacts with them in an abstract way. It asks, how many devices do you have to execute this image? And it provides some of the image. And then the plugin says, oh, I have 4 devices available for this image. And the next plugin says, I have 0. And the next plugin says, I have 150. So that is how LibOhm Target comes to the, like, how many devices are available by asking the plugins. And it asks them on like generic levels. So it can also say, hey, please copy this memory to that device at that address, and so on and so forth. But it doesn't know how that is done, all abstract. And now we have this RPC plugin that we put in there that we ship with LLVM. And that RPC plugin is actually going to connect to servers that can be on the same host in a different process, or on different hosts, in a cloud, in your cluster, whatever. And whenever this one gets a request from LibOhm Target, any request, doesn't matter which one, it will ship it through the network to this server. And what the server does, it basically asks the plugins on the other side, including the CUDA plugin, on the AMD plugin, this question. And then it accumulates the results. So when the LibOhm Target asks the RPC plugin, how many devices do you have available for this image, for this object file, right? We ship that through the network. On the other side, we'll ask all the plugins, hey, CUDA plugin on this side, at this computer, here's an image. How many devices do you have available? So the LibOhm Target thinks it talks to the CUDA plugin effectively. CUDA plugin thinks it talks to LibOhm Target, and they kind of do. We just, cross the barrier through the network, right? And we have 2 implementations for this. One is upstream. The other one is like for a long time about to be upstream. One is based on gRPC, like Google Remote Procedure Calls. That's upstream. And then we have one that is based on UCX, which is on the thing that is MPI usually implemented on top of. And then there is nowadays also an MPI implementation mode, but that lives somewhere else. And there's going to be a paper about how some people took this and improved, like analyzed the performance and made it actually, performant and good, rather than what we initially did with this, which was working, but they kind of improved performance and so on. So we have a paper that I won't about this. Cool. Yeah, if you want to read ISC this year had this paper, like the main one. Go back. I'm running out of time, and I have so much, like at least a few really cool things that I wanted to show. OpenMP is intermediate layer. This is work that we done this year. It's going to be published at PACT in 2 weeks. At least it's accepted. I hope that it actually makes it into the proceedings. And I'm going to explain it out of the OpenMP perspective and give a little bit of context. This is how, you can't read, the colors don't really, you can't really see the colors. Anyway. So this is the compilation toolchain simplified for OpenMP offload. Clang makes a device and host compilation. We take the OpenMP device runtime in the vendor runtime, link it into the device code, embed it. At execution time, we use the vendor runtime to offload it to various targets. Yep, we've seen that a couple of times before. We don't support Intel GPUs just yet, but we're working on that. So all of that will effectively apply for Intel GPUs. And then this is where we actually came up with the LLVM thing. So we have not only the OpenMP runtime, but we also have a LLVM that has multiple targets included, and we embed that. Okay, cool. Now, I told you before, now you can link together CUDA and OpenMP code. So you can, from OpenMP, you can call in CUDA device functions. So if you have a random number generator implemented in CUDA, really fast, really cool, you can call that. So that is one thing. So you can have this, we allow it through the new driver and the new embedding scheme, and like by basically using the new driver also for CUDA and changing everything to use the same embedding, like with the sections and the section names and how globals are registered and kernels are registered, and how you merge the different device codes at device LTO time. By doing all of that, what I talked about earlier, piecewise, we allowed to call CUDA code from OpenMP, CUDA device code from OpenMP random functions, including also things like thrust, the device versions, and cub. Okay, cool. So far, so good. Now, at this point, you can already call CUDA from OpenMP. OpenMP is portable, right? Why is CUDA not portable? I mean, right now, if you take a CUDA compiler, they will tell you, oh, you can compile this for NVIDIA devices. So what is missing to make CUDA portable? So one is you have the CUDA API, which is only implemented to work with CUDA, like NVIDIA devices, like CUDA memcopy, CUDA malloc, all of that things, right? So you actually need them to be portable. So you have to wrap them, or you have to kind of remap them, re-implement them effectively. And then you have these built-ins, for example, threadid.x, which or __ thing threads that we've seen before. Those things are also, like some of them at least, are inherently CUDA-esque. They are NVIDIA specific. So you have to deal with those. But turns out you can. You can wrap both of them. And then you basically at compile time, when you compile CUDA code, you do not include CUDA headers. Like if the user writes include CUDA.h, what they get is our header, not the CUDA header from the CUDA installation. They get our header, and our header implements CUDA malloc by calling OpenMP device alloc. Our header implements CUDA memcopy by calling OpenMP target memcopy, and so on and so forth. So you get the idea, right? So we implement the CUDA API through OpenMP, to portable OpenMP functions, existing and new ones that we added. And we implement these built-ins, like threadid.x, through OpenMP portable functions like get threadid in block, like OpenMP get threadid in block, which then effectively, if you target actually CUDA, translates back to what it would have been originally. But if you target AMD, it translates to something else. So by adding these wrappers, we effectively make CUDA portable. And then we take the CUDA code, including the kernels and kernel launches, and we utilize an existing offloading library that is portable. Basically, the CUDA kernel launch now becomes, OpenMP launch kernel, conceptually, right? There's a little bit more tricks there, but that is the idea. We wrap all of the existing user-facing API and the hidden APIs to launch kernels and so on and so forth. You could do this with, or we will do this with HIP and SYCL and so on and so forth, but for now, it only supports, CUDA and a subset of the API, but proof of concept is there. And so a lot of these things
So Johannes, when you do that, are you using like an include overlay? Is that how you implement that?
Yes.
So you intercept it and then you actually call the real one? No, we do not. We intercept it, yes. So if you do include CUDA.h. How we do this is we actually introduce another include search path. And then you do the include next. Okay.
No, we actually don't include next here because we actually do not want to contaminate our environment with actual CUDA headers.
I got it.
But
So you're actually then calling your library routine. Okay.
we translate all of the things that we support, we have to translate in our headers as they are. And everything that we don't support will cause you a compile error. And then you can add support.
All right, cool trick. Thanks.
And why would you do this? I mean, one way of doing this is you've heard about this virtual GPU that we have that you can, run your GPU programs on the host. I mean, now you have CUDA that runs through OpenMP layer. OpenMP has this virtual GPU that runs, software on the host. So composable, here we are, a CUDA code unmodified that runs on the host, and you can attach GDB to it and breakpoints and all of that good stuff. Well, and it's not that smart. It's actually just fun. So this is, so this one rig. So you can actually offload CUDA to the host and debug it there, right? Cool. You can also make it portable. So you can take CUDA code and run it on your AMD GPU without modifying the CUDA code whatsoever. This is XSBench again, one of our favorites. Such a good benchmark. Vendor CC is the native compiler from the vendor of the hardware. This V100 is NVIDIA, so this is NVCC. MI50 is AMD, so this is a HIP-CC. Okay, that is the vendor's provided compiler. ClangCC is using Clang as a compiler for CUDA. And here we, like vendor CC and ClangCC actually compile the HIP version of the code, not the CUDA version, right? CUDA OmpCC is using Clang to compile the CUDA code through OpenMP and offload it through the OpenMP layer. And here it does so too. It doesn't compile the HIP code, it compiles the CUDA code. So these two are HIP compilers. This one is a CUDA compiler. And for XSBench, I show you that first because we're faster than the others. So that's great. Part of this is because we run this through the LTO toolchain, and when we did the experiments, the others didn't have the LTO toolchain. Like there was no device LTO for CUDA. The other thing is when you enable OpenMP, you run the OpenMP op pass, which you don't otherwise run. And the OpenMP op pass can sometimes just improve your performance of your program as well as a side effect, which is good. But we also have different other benchmarks, like Lulesh, for example. NVCC is much faster on NVIDIA than Clang as a CUDA compiler is. But we, as a CUDA compiler, we take CUDA code through OpenMP and compile it for NVIDIA again, are comparable to Clang as a CUDA compiler. So that's good. So we don't actually introduce overhead by going through this, sham layers and going through the OpenMP runtimes. On the HIP side, like AMD side, the HIP compilers, HIP-CC and Clang as a HIP compiler perform equally well. We perform worse. Why? Because Lulesh uses streams. And our AMD plugin currently does not support streams. So we lose out on that. Once we support streams, and we're working on that right now, we'll get that boost. Yes, we translate them as well into generic target independent versions that we then implement for all the targets we support inside the device runtime. Not if you do device LTO, because we can fold it all into each other and it ends up exactly what you want it to be. Because these are just sham layers that are effectively, this function is return the other function. The inliner will make, has no problems with getting rid of all of that stuff. Oh yeah, I would. As I said earlier, you should not mix multiple offloading programming models in a single file. But and at that point, you realize, okay, LTO is for certain really good. Even if you could mix multiple programming models in a single file, yes. I mean, I would always enable device LTO if I were you from now on till the end of time. There is one reason not to do it, and that is compile time. And right now, most people do not have enough GPU code that it matters. Once they do, we will have come up with a solution for this, believe me. Yeah. Before we run out of time, I will tell you about the latest thing we did, which is also fun. I mean, the other thing was already fun, but there's a lot of fun things. This is like direct GPU compilation. So I made these slides last night, so it's not great, but I'll explain it, and then you'll understand. How does OpenMP offloading, any offloading work? Okay. You have a program that runs on the CPU, and the user orchestrates data in memory movement to like with kernels and explicit data transfers, and those kernels then run on the GPU, right? So the conceptual idea is, I have a program, my world is a CPU, and sometimes I want to offload something to a GPU because CPUs came first, and I don't know, that is what it is. So we are CPU centric, and we use offloading devices that we offload to. Now, anyone has a good reason why? Why do we start our program on the CPU rather than the other way around? Thought so too. So let's turn it around. We take a program as it is, no modifications whatsoever. A CPU program, effectively, if you want, right? We take a CPU program. There's no offloading in there. So we just take an OpenMP CPU program from 20 years ago, right? Before any GPU stuff came up, before anyone thought about it. We take that and we compile it directly to run on a GPU as a whole. We don't modify it, we do none. We just say, hey, compile this program as it is to run on this on this SM80 architecture. And we provide a little bit of wrappers because we really like our wrappers. That's our thing. So we provide a couple of wrappers and we modify the driver to include a couple of files and include files into your link in headers into all of your source files, and we also include another file to make things work. But effectively what you do as a programmer is you specify one flag to enable the whole shebang that says, OpenMP direct compilation or something like that. And then you specify what the GPU architecture is. That's it. So it's really not much of a burden on the user. So you just say SM80, and I want direct GPU compilation. And then your program is going to actually, it's still starting on the CPU, but you don't see that part. Your main function starts here on the GPU. And all of what happens now is we execute this code on the GPU. And whenever we encounter something that we can't execute on a GPU, the idea is to kind of reverse offload. So we basically make a sys call, we make an RPC call back to the host and say, hey, host, can you execute this for me? That is obviously the tricky part. So in the first, we have this at the LLVM HPC workshop at SC. You can hear more about it. We basically had 30 or so host libc functions that we implemented. So fopen, fwrite, fread, and so on. And some of them were implemented only on the GPU. Others were implemented on the host, and there was communication. But it was manual. We had to implement them one by one, which is unfortunate. We're currently working on the alternative to not implement them one by one, and everything just works. Let's see. So this is kind of the idea of what we do. Direct GPU compilation. So GPU is your actual direct target, and performance is horrible. It's really bad. The GPU is slower than your CPU, and even if you can use the parallelism, by default you can only use parallelism in a single block, because you have to but the parallel will just translate natively into a parallel on a single block. And because you move entire programs there, your register count is out of this world, which doesn't even allow you to use all of the threads available, maximum number of threads. So effectively, you run with 256 threads, maybe, which is not that much more than the CPU has, and all of them are slower. So this was really fun. And we're okay, what could we do? One thing that what we want to do is we want to use the entire parallelism on the GPU. So when you have a parallel region, Under certain circumstances, you can actually offload it to the entire GPU, multiple blocks. You can't always do that because the synchronization reasons, communication reasons, but under certain, like a lot of times you can. So what we did is we effectively like analyze and do this transformation from a parallel 4 to a target teams distributed parallel 4. Now, as you see here, target teams. So that basically spawns a new kernel. Yes, we split off the parallel regions into new kernels. And when we hit them, we execute the new kernel. So we execute the main function with a single thread and execute a new kernel with hopefully a lot of threads and a lot of blocks. In that, initial performance testing show us that now on the offloading parts, we are on par with manually offloaded, implementations and so on and so forth. But we take 20-year-old CPU code rather than doing anything. So it's kind of cool. Okay, I'm actually almost at the end. How did this work out with the time? It is unbelievable. Okay, where next? These are my last 2 slides. This is a rough idea of how the compilation, like OpenMP compilation in the LLVM land looks like. You have OpenMP as an input. It goes into Clang and Flang. Effectively, they go through the OpenMP builder, or will eventually go through the OpenMP builder to generate LLVM intermediate representation with OpenMP runtime calls. We have OpenMP aware optimization that then run, and then we generate. We kind of interact with the OpenMP runtimes to run it on all these things with all these goodies like profilers and virtual GPUs. So this is kind of where we are right now. Flying takes this detour through MLIR, which in this context is not that important. What is interesting, though, is where we're heading, or at least where I want to head. And then it looks like this. And this is a little crowded, so let's try to look through it. On the left side, you see all the different inputs now, programming languages and other things. What I'm trying to say here is, if you think OpenMP, forget the pragmas. So little of the OpenMP infrastructure in LLVM deals with pragmas. It's ridiculous. Pragmas are the first thing we get rid of really fast. And then there ain't no pragmas anymore. You don't need pragmas. Alternatively, OpenMP is like this whole ecosystem. And languages like Chapel already look at using OpenMP to do their offloading bits. They implemented, initially they had like an NVIDIA offloading backend for Chapel. Cool. And then they realized, oh, now they need one for AMD and probably for Intel and maybe some other things. And then they're like, if there would be a portable runtime that we could target and that would then do the translation for us to all the different other ones. So I talked to them and they're now trying to target, or already targeting, but trying to get it into production, to target the OpenMP runtime, which is, as we've seen with regards to the CUDA example, a portable offloading runtime. And then you can, like, you don't have to write all the backends yourself. We provide them. We also provide the device runtime implementation. And it doesn't matter if you come from OpenMP target regions. You can come from CUDA, as effectively shown. You can come from Chapel. You can come from other things. OpenACC to OpenMP translation happens through Clack and Clang and is part of Flang. So Flang will support OpenACC, and there's a lot of work going on to support those pragmas. But there will not be an OpenACC, standalone runtime or standalone like offloading ecosystem. It will all go through an extended OpenMP runtime, OpenMP device runtime, and so on and so forth. That's already, discussed. CUDA was shown that you can use it to target OpenMP runtimes. HIP-SYCL is the same thing in blue. If you have DSLs, you can basically also go to, parallel MLIR, and then use the OpenMP builder to lower this generic parallelism to OpenMP parallel. Why would you do all of this? This is the important part. All of this, the generating the code, the optimizing the code, and the runtimes, those are the heavy hitters. Those are the parts that are kind of, you spend a lot of time dealing with. those runtimes that talk to all the drivers, those runtimes that orchestrate all of the things, and so on and so forth, that provide you with all of those features to do profiling, to do like debugging, and so on and so forth. Those are shared. I mean, that is not only you don't have to implement them when you come to Chapel. No, that is also your code is now interoperable. You can link together and LTO optimize together Fortran OpenACC code with CUDA code, with HIP C++ code. Merge it all together, scroll it a little bit and run it. So if your application developers want to write some parts of the kernels in this one and some parts of the kernels in this language, why not? Let them. It's all syntax. The front end is the first thing we run, and it removes most of the syntax stuff anyway. So at that point, the question becomes, why do we kind of try to split it up? We have to converge our ecosystems, especially on the runtimes and the optimization parts. And that's what we're doing here. And that is what I'm going to stop with. Thanks. Any questions, comments, concerns? None? Anyone from the audience on Zoom? Kent, are you still there?
So this is kind of this last chart's kind of your vision chart, right?
Yeah, I mean, you see the color coding, right? It's not like we implemented a lot of those errors already to some degree, and especially under development means they're committed. Like those things are not researchy prototypes, but under development means there's commitment behind them. So they will happen, very likely. The blue ones are the ones that are more of a, we tried it out and it seems to work. So we actually have, there is Python number to OpenMP builder to OpenMP runtime. So OpenMP annotations in Python code that exists. So the blue ones are, yeah, we tried it out. It seems to actually work. And only the yellow and the orange one are, though it's actually not true anymore. Chapel actually has a research prototype. So yes, my vision, but a lot of it is actually, on its way already. Is there questions in the chat, maybe?
That's a big vision. This is Kent. That's quite a bit. That's a lot.
Okay, it doesn't seem to be.
Yeah, I'm trying to get the thing that happened in the thing about software, application software, is it's intended to last for multiple hardware generations. In fact, in a lot of cases, it's intended to last indefinitely. So speak to the fact that the OpenMP has got to live in the code, the user's code's got to span different, and you have all these different other programming models here down the left side, but they come and go, and will they be supported on all the different hardware? And I think what you're getting at is there are ways to make this, to get a broader support for some of the more domain specific, say, languages, right?
I mean, I'm
trying to kind of get the picture of longevity here, right? Like how to, because that's kind of the problem. And if we have an environment that doesn't, and that's one of the motivations of OpenMP is to get a standard that will last for several generations, even though we keep adding more to it, with the standard. But the idea is to make something that will last for a long time, right? Your application can be written and then portable between hardware platforms. I mean, without standardization pieces, we don't get that long-term effect.
Right. I mean, it's true. And some of our experiments that I showed in the end, like direct GPU compilation and the portable CUDA, are to show that you might actually, this is a way to get this for things that are old. Like CUDA was extremely successful as a GPU language, but now we need portable languages. So everyone is is teaching, oh, we have to, use high-level abstractions or portable languages and so on. But there's still a lot of CUDA code out there, and I can understand the people that don't want to port it. And I don't think necessarily they have to. And the same, like with old CPU applications. I mean, we might get people that now, optimize them or relook at them. But what if we could run them at, I don't know, 60, 70% GPU performance, like peak performance, without doing anything? That totally changes the equation on how much time and effort we're willing to invest, but also that opens up a whole new world in what to do with old applications. And you can then mix and match them and optimize the parts that you really need to optimize rather than spending time with, trying to understand all of it. Some point. Cool. Any other questions? Last call.
Well, it's just a comment. Thanks, Johannes. This is good stuff.
Welcome. And then I'll put the recordings and the slides online. Michael has my consent on both, and coordinate with him.
Yeah, hold your horses on that.
Sure. Can we get a hold of the slides right away? Michael?
Yeah, I can actually, wait, let me share it in the chat. Let me share the link in the chat. That way you can.
All right, but the recording has to go through the ARB, unfortunately. Sorry about that.
But the slides don't, right?
Yeah.
Can you use that link? Oh, there's a question in the chat. Do you think that LLVM is the best place for OpenMP aware optimizations? Short answer, yes. Longer answer, it depends. It depends on how long you want the answer to be. Is it the best overall place? If I could start from scratch and could have infinite resources, maybe not. But it is the right place given the circumstances in the world in which we live. The people that like the alternative that everyone is, teaching, like telling me for the last 3.5 years, is, oh, why don't you use MLIR? This is the new thing that Google announced and that is so hyped, and every second compiler paper uses MLIR because it's the cool buzzy thing. So that was 3 years announced. 3 years ago was announced, right? Show me a non-machine learning application that uses that in production. There's none. So if we moved there 3 years ago, we still had no production optimization for OpenMP right now. And there is no clear timeline on when C++ is supported through that pipeline, if ever. And now you could say, okay, but let's assume it is at some point. Isn't that a better level? There are benefits to it, but one has to understand that it is a representation and nothing else. Representing things in MLIR is a representation choice. There are certain things in MLIR that are that make it inherently easier to reason about stuff. But one of those things that people always associate with OpenMP, the outline parallel functions and so on and so forth, are, funnily enough, not one of them. The part that we outline a parallel region into a function and then go through the runtime is actually not a problem. The real benefit of MLIR, if you ever get into a discussion with me, you should say the type system, because I can't argue with that. That is actually helping you to properly add things. But given the fact that we come from C++, or I come from C++, I don't need a stronger type system. My type system is weak to begin with. So that actually doesn't help me. That helps you if you come from a DSL, like a high-level DSL that has properly defined multi-dimensional vector, like tensor types. Then this is cool. But if you start with C, it's not helpful. And then really just the fact that in MLIR, you can now define the parallel region as an inline operation in which directly uses the values that are, surrounding it. So basically the parallel code is in the same function in quotes, like the sequential code. So it looks like on the source code level. That is only on the surface really helping you. It's absolutely not necessary. It's a representation choice. It's effectively as if you represent a function like the thing that we do in LLVM IR inline. So it's kind of just a choice how to print it. I could print it. I could print LLVM IR like that too. You don't actually gain anything by it, effectively. And I know my opinion on this is controversial, and it has in the beginning. If you go back to the very first talk about MLIR, Euro LLVM 2018, if I'm not mistaken, in Brussels, and you scroll to the end of the talk, I'm the one that asked the mean questions. So you might want to start there if you're interested. Okay, I think this is it. Thanks everyone, also the people at Zoom, and thanks everyone here. And yeah, I'll be here for the rest of the next 2 weeks. So please feel free to reach out.
Thank you, Johannes. Great tutorial.
Thank you.
Bye.
Thank you.